Elena, ya está grabando. Ahí ya pusieron a grabar eso.
Sí, sí, ya estamos, hace rato.
Okay, so welcome to the first session of Wednesday. And remember that after these first three talks, there is the group photo that we're gonna take. So everybody will have to connect the cameras. And Elena will take the photo. And the first speaker is Jose Edelstein from Santiago de Compostela. He's gonna talk about aspects of geometric inflation. So go ahead. And please mute your microphone if you're not speaking.
Okay, thank you very much, Martin, and thank you all the organizers for carrying on these difficult workshops in which we all have to connect from different places. So I hope you're watching my screen because I had some problem before, but hopefully yes. If you're not complaining, that means yes. I'm going to talk about some recent work that was done with these people that you can see below the slide. Gustavo Arciniega and Luisa Jaime at the beginning. Then we joined the efforts with Pablo Bueno, Pablo Cano, and Robbie Hennigar. And finally, in the last month, I published, we submitted to archive a couple of articles with my students, David Vázquez, Alejandro Vilar, and the last one with Robert Mann last week. So let me tell you the idea. Oops. Okay, now it works. So the idea, I will be dealing with higher curvature corrections to GR. We know that, it's a standard law that GR is a low energy effective description of gravity. And one possibility, which is also, I would say, is also part of the standard law, is that the corrections to the Einstein-Hilbert action are also given by a whole series of higher curvature terms and covariant derivatives of the Riemann tensors, etc. This is, for instance, what happens in string theory, and this is the canonical expectation of an effective field theory of gravity. And the idea is that there is a scale, which I will call all along my talk L star. This is a length scale, or lambda star, if I'm talking about an energy scale, which is suppressing the higher curvature corrections Rn. So I will be working in 4 dimensions with, in principle, I will not use the cosmological constant, but okay, here it's written there. And then the idea is to have all possible terms of up to, the whole series with dimensionless coefficients lambda n, and the dimension full part is given just by the right power of the L star. So I will tell you about my rationale behind the construction of this Rn in a second. Typically, the least thing we expect is that these Rn's are Lorentz invariant and diffeomorphism invariant, because we don't expect those symmetries to break at low energies. And there is a canonical, so canonical that there is a paper in the 19th century by Ostrogradsky, not in this context, but in the context of classical mechanics, in which he showed that typically higher derivative terms entail instabilities of the ghost kind, in the sense that you have degrees of freedom with the wrong sign in the kinetic term. Now, LAWGH, much more recently, although many decades ago, he studied what's the most general thing we can write at every given order in order to avoid the Ostrogradsky problem. And he found out that to each order, there is a single term that you can write that leads to second order Euler-Lagrange equations, thereby has no ghosts. Unfortunately, in 4 dimensions, the only term is LAWGH, is Einstein-Hilbert, at the cosmological term. So basically, the whole LAWGH program finishes here in 4 dimensions. So if we want to do something in 4 dimensions, we have to go to do something lower strict than LAWGH demands. So my demands on the Rn's would be the following. I will first, the action must have a maximally symmetric vacuum, like the zeta and the zeta flat space. And when I perturb around that vacuum, I expect to have only massless gravitons. In general, you will have also massive gravitons with the wrong sign of the kinetic term. I will kill them, and I will also kill the scalar degree of freedom that also generically arises. I can kill both fields just by a convenient choice of the Rn. Then I will demand also that the black holes are well behaved in the sense that they have positive mass and well behaved thermodynamics. These two first points were carried out already by Pablo Bueno and Pablo Cano before I started to playing in this game. And then basically the addition that was done in the papers advertised in the front page are including a well-posed initial problem for cosmology. And by this, I mean simply that if I write Friedman-Robertson Friedman-Lemaitre-Robertson-Walker ansatz, I expect to have second order differential equation for the scale factor. So if you try to see what can you write with these conditions, at quadratic level is simply the Gauss-Bonnet combination, which in 4 dimensions is topological, then it doesn't contribute to the dynamics. And at the cubic level, there is a single combination, which is this one, P minus HC, where P is this combination of the cubic Riemann tensors that was found by Pablo Bueno and Pablo Cano, and for a good reason they call it P, a few years ago, in which they showed that basically, well, the first 2 points are fulfilled in this for P. And then there is a second possible Lagrangian, which is this Lagrangian C that was identified shortly after. And in principle, it seemed to be trivial because in any Einstein space, it identically vanishes. But it turns out that in cosmological setups, it's necessary to keep the equation second order. So actually, this combination you can show that fulfills the 3 conditions I put in the top of the transparency. Now, even if the cubic case is unique, which is of course tantalizing, if you go to higher orders, the uniqueness does not take place. I mean, for quartic order already you have more than one possibility. And actually the degeneracy of these densities increases with n quite quickly. This is, well, this is something that of course it would be amazing if there is a unique action that satisfies those conditions, but the good thing is that it's not that easy to build these densities because they are so degenerate when you go up in order that even if the amount of terms that you have to combine also increases a lot, but the combination of the degeneracy increase and the number of terms increase is actually tractable. So you can in Mathematica go to order 10, it's not difficult to go to order 10. Now, so I have a theory that depends on an infinite number of coefficients. So this in principle is not the best starting point for a phenomenological proposal. But of course, one possibility, which is of course in the back of my mind, is the possibility that there is a single theory, like string theory, from which you can compute all the lambda n's. So actually in that case, there would be no parameter. All parameters could be obtained from the theory. But given that I want to stay as much as possible independent of string theory, I will keep the lambda n's independent, and I will try to look for, to make conclusions that are as much as possible lambda n independent, in the sense that I'm not going to choose something very fine-tuned, but basically a generic situation. With some exceptions, for instance, the one that mentioned here, for generic lambda n's, you can have an infinite number of vacua, and this creates a mess, and it's quite difficult. And actually, we explored with Gaston, who is connected there, and these people some years ago in the case of LAWGH theories, and there is a beautiful dynamics, but of phase transitions, etc., between different vacuums. But I'm not willing to go to that point today. So I'm going to assume that there is a single vacuum, or all the physics I will do is around the vacuum that is connected to Einstein, to general relativity. That means the one that, if I turn off all the coefficients, goes back to the vacuum of general relativity. So there are some constraints that one have to be careful about. For instance, quadratic and cubic terms in the Riemann tensor have to vanish, at least unless C1 and C2 are ordered, these coefficients are ordered the Planck scale. If not, some causality issues arise. But these causality issues only tells you that you have to add some matter fields. So I hope I'll remember later when I will do something which is quite reminiscing of including those terms later. So let me go to the point. So I have this, my action. I will put the Friedman Lemetre-Robertson-Walker ansatz for the flat topology. And I will work instead of working in the time variable, I will work in the e-false variable, which is quite convenient and done typically in cosmology. And this is something that is usual, customary. So the translation between derivatives is simply given by the fact that the scale factor is exponential in the number of e-false. So, and the good thing of these theories is that the Friedman equations are very, very easy. Actually, there are, of course, two Friedman equations, but you can forget completely about the second one because as it happens in GR, the first Friedman equation plus the conservation of the stress energy tensor are sufficient to derive the second one. So actually, the two equations are these ones. It's basically the first Friedman equation and the conservation of the stress energy tensor. So this is an algebraic equation H, which is, of course, well, if f of h is a complicated function, it can be very difficult to solve, but it's not even a differential equation in terms of h. And f of h is a generic function in which you can see the lambda n's appearing, of course, at each order. One surprising thing is that shortly after we submitted our paper, there was a paper by LAWGH and Barton-Suivach, in which they showed that in the context of double field theory, a cosmological setup in which you impose T-duality, well, double field theory is the right canonical setup to deal with T-dual invariant theories, then the cosmology is also given by a function exactly of the same form as the previous one. This doesn't mean that I know how to relate both things, because in particular, the Hohmann-Suivach result is in the string frame. Actually, if you go to the Einstein frame, this was done by Krishnan shortly after. And in the Einstein frame, the situation is a little bit more difficult, and f of h exists and satisfies, it's constrained by a second order differential equation. But it's surprising, and I think also it's a positive surprise that string theory seems to, there seems to be a place to accommodate this in string theory, although, again, I'm not necessarily implying that. The cosmology is entirely given by this function f of h. This is, if you want to see something like this, you can go to Xian Camaño's thesis. It was never published in a paper because in LAWGH theory, the cosmology is a cosmology in higher dimensions, which is something that is not very interesting. But the formalism is the right one to deal with this. So it's a cosmology depending on an infinite number of parameters. There are some, I told you that there is more than one density that satisfies the criteria I am imposing in my theory. And the good thing for the cosmological setup is that if I find any couple of different densities are related by a term whose contribution to the equations of motion is basically h to the 2n. So if I have two densities, using density A or density B simply amounts to choosing the coefficient of A or the coefficient of A plus B. Since I don't know the coefficients, so for me, the degeneracy is completely irrelevant. All the ambiguity of the choice of R is simply reflected in the ambiguity in I don't know the values of lambda n, and I can choose them as I want. Now, there are some constraints of f of h, as I mentioned earlier, not exactly in this context, but okay, you have to, f of h has to give reasonable physics. By this, I mean positive mass black holes, for instance, and it's useful to avoid having f of h having critical points, because typically there you can have singularities. This is not a dramatic problem, but I'm willing to evade it. Now, the initial work on this field was with Gustavo and Luisa in the cubic theory. So we choose the single Lagrangian at the cubic level, and we add radiation, and we found basically that there is a cosmic inflation in the early universe just by the introduction of the cubic term without a scalar field. So this was surprising at the beginning, at least to me. I think to us. So we call this geometric inflation because it's simply, well, you need radiation to trigger inflation, but basically there is no need of slow roll regime or a scalar field or whatever. I will come back to this point later. Now, in order to, well, when I saw that Juan was going to talk about cosmological wormholes, I felt myself at home, because at the beginning I thought, why I should be talking about this in this conference. It's a little bit off topic, but in his talk, there was also the word cosmology. But then when I saw the two-dimensional cosmology he talked about, I'm not sure if this is still a consolation for me. But anyway, let me tell you that these kind of theories are also interesting in the holographic context. There is this beautiful application of these people in which they show that the free energy in a squash sphere of a three-dimensional CFT in a squash sphere, they were able to show fully within the Einsteinian cubic gravity setup that there is this formula relating purely CFT variables, in which you have the central charge and you have the T4. The T4 is a coefficient appearing in the three-point correlator of the stress energy tensor. So then this formula, if it's possible to compute it from the bootstrap technique or any other technique, this is a formula that is completely written in terms of CFT variables. And so this formula either is correct or wrong. And it's an interesting prediction of holography in the context of these theories. So shortly, let me go to a couple of comments about the cosmology that we found. You get the Friedman equations can be solved parametrically. And for instance, if you truncate the series to a given order, then it's quite easy to see that you have this solution. And in particular, I'm going fast here because I want to spend, I don't know, 10 minutes telling you the papers of the last month. You can compute the epsilon slow roll parameter, and then you see that this is 2 over the maximal order at which you truncated. So then if this order is greater than 3, greater or equal than 3, then you have epsilon below 1, which is the sign of inflation. So all these theories, starting from the cubic one that we discussed with Gustavo and Luisa, they all inflate. Although the inflation is polynomial rather than exponential if you truncate the series. But of course, if you, you can argue that it's not consistent to truncate the series, because whenever you truncate it, typically you have, I don't know, a given n max, the maximal order is, the curvature is so large, you can easily see that it's so large that the coefficient n plus 1 will be the same order as the coefficient n, and actually you have to include the whole series. But this is good, because when you include the whole series, you get an exponential, nearly de Sitter inflation. This was explored in this paper with De Pablos and Robbie Hennigar, in which we show the different possibilities for the function f of h, and we checked that all of them basically gave the same physics. So we cannot prove a theorem showing that, but basically you put whatever function you think of, that satisfies the previous constraints, and then you see that you have exponential inflation. For instance, with this function I wrote here, you can see that the behavior of the scale parameter close to t going to minus infinity, because since inflation is exponential, there is no Big Bang, there is no initial time. Well, you see that basically the canonical, the red curve is a GR, and then you see that the blue curve basically sticks very close to GR very quickly, but it departs from GR in the early universe. And here you can see the epsilon parameter. You can see that you can have easily 60 e-folds of exponential inflation. However, I will show that, next that there is a problem with this setup that I would like to solve. So this will be the motivation for the last two papers. So so the first problem is actually a problem that was found a couple of months ago by these people, Starobinsky and collaborators, and they saw that if you turn off matter and then you look for the Sitter vacuum of this theory, that they actually concretely took the cubic theory, and they chose the given root h constant, which is a root of the polynomial f of h, of the cubic polynomial. Then they saw that even if the Sitter solution is stable, if they stable naively, I mean, if you simply perturb it, but keeping the symmetry of the solution, it's stable. But if you perturb it in an anisotropic way, it's not stable. So they show that it decays in less than an e-fold. So the a cosmology built on top of a root of f of h is not a good idea, apparently, at least in the cubic case that is the one that they carried out. So this is one point to have in mind, but luckily we had a different point in mind that also made us think that there is something else we have to include. So even if naively you can get rid of the scalar field, then it's quite easy to see that there is a generic problem, which is the following. You can take the function, so the Friedman equation is 3f of h equals to rho divided by m Planck squared. So you can always, the GR coefficient is the 1, and then you can just split the series in this way, in which you have GR and everything which is beyond GR is this function G. So if the accelerated expansion driven by radiation is not a GR issue, a GR feature, I mean, in GR, radiation does not inflate. So then basically the accelerated expansion will happen when G is much greater than 1. Then also, in order to connect to GR, we need that G goes to 0 when H goes to 0. So basically, there are two stages for inflation, which is when G is much greater than 1. You have let's call it the Heidegger curvature era, at which accelerated expansion happens. And then when GH is much lower than 1, you have the GR-ish regime of the late-time universe. So let's, just to have a reference, let me call H end the value of G such that G of H is equals 1, which is roughly the division between these two regimes. Then you can easily see the following. I mean, if you assume that inflation is driven by any barotropic fluid of coefficient W, that means P equals W times rho is the equation of state. And then you write basically from the Friedman equation here. So when Hn is 1, 1 plus 1, 2 times 3, 6. 6 is equals 1, basically, roughly. So I am removing the 6 here. So you see that the density at the end of inflation should be given by this, but the propagation backwards in time is given by this rule. So then you can see that the initial density grows when you go backwards in time, grows a lot, grows exponentially. If you want to keep the initial density below the Planck density, which seems something reasonable to do, then you need that the Hubble parameter at the end of inflation should be constrained by this expression here. It's a simple computation. So then you can go to, so H of n, you expect H of n to happen closely at the point where GR becomes the right theory. So the astrophysical constraints on L star, the coefficient driving the Heidegger curvature terms, is quite poor. It's this one here. So then you can see that H of n has to be above this very low value of the energy. And if you take lambda 3, which is a dimensionless number that goes in front of the cubic term, order 1, which is like the natural expectation. If you have to put a very large number or a very small number, it's not fair to play that game. So if you take this order 1, you can see that if you put in this equation, you put radiation and 60 e-folds, you have that at the end of inflation, if you have a sub-Planckian density and 60 e-folds, you have a final value for the Hubble parameter, which is basically ruled out by this constraint. So this is not enough. We need something else to cure this problem. This is written here. The exponential expansion is so extreme that you need really a large energy density at the beginning to have something remaining at the end, which is consistent with the fact that at the end you must be in the GR regime, and the GR regime cannot appear at whatever energy scale you want. I mean, there are some astrophysical constraints. So then you need something preventing this to happen. You need some fluid that does not dilute so fast. And this is actually the same reason behind the introduction of the inflaton. You need the inflaton is the scalar field whose equation in the slow roll regime, whose equation of motion then is P equals minus rho approximately. basically does not dilute as a cosmological term. So then let's go to the garbage and pick the inflaton back and put it again. So then I put the action for the scalar field action.
A 5-minute warning.
Yeah. So these are the density and the pressure, and then I coupled it to the cubic theory. And then, well, so I will go to basically to the plots. You can see that if you don't put radiation, the cubic term basically spoils the slow roll behavior. The red curve is the GR case, and then if you turn on the cubic term, the bigger is the parameter in front of the cubic term, the faster the scalar field plumbs to zero. So basically, the cubic term spoils the slow roll behavior. So then we are going to explore these possibilities to cure this problem. One is including radiation. I will show very quickly that this leads to a hybrid scenario in which there is some part of inflation which is geometric inflation. I call it Bandonian-like geometric inflation because of the Latin American nature of this workshop. And then there is a final regime in which it's the canonical inflation. And another possibility would be to push inflation to much higher energies, as I will show very quickly. So imagine if I put radiation, this is a term that has to do with radiation. I'm going to just show a plot because I have 4 minutes. In this paper with David and Alejandro, there is a whole discussion of the analytic handling of all regimes, the verification of how they paste together one with the other. So I will show you a plot, and all the mathematics that is behind that plot, you can find it in the paper, but I think the plot is clear enough to be explained directly. So this is a plot of the quartic theory, in which you can see here the quartic, cubic, and GR contributions. The GR, sorry, is the horizontal line here. You can see which one is the dominant one whenever the curve is above the other. So up to this point, you have quartic inflation. From here to here, you have cubic inflation. And finally, you have GR with an inflaton field. So you can see that the quartic inflation is very epsilon. It's practically decoupled from the cubic inflation. So here, basically, you have while the quartic term is inflating, you have epsilon constant, which is the prediction of quartic inflation. The scalar field is almost constant, which is this is unexpected. And then basically you have the transition to cubic inflation when the curvature is lower. Here, it's not that the plateau is not that clear as here, probably because the period is very small. But the scalar field stays constant until GR enters into the game and the scalar field start to go slow roll down the potential. This is surprising because naively one would expect that if you play with equations, you would expect that the scalar field does not stay constant while the higher curvature terms are at play, are active. And then in principle, you would expect that the scalar field, whenever GR enters into the game, the scalar field already spoiled all its energy in rolling down the potential, but without producing inflation. This is not the case, surprisingly. And you can go to any order, and you can see that this Bandonian-like cascade means that if you put here, imagine that you go up in order, you will have a sequence of periods of higher curvature inflation, a decreasing sequence. And actually, like if you have a Bandonian that you push and you put all the steps of the Bandonian all together. And at the very end, you will have ordinary GR inflation, which is a nice feature because then the reheating story and all this thing would be exactly as in GR, or at least we expect this to be exactly as in GR. Let me shortly go to the other possibility, which is pushing the inflation to a very large values of the energy. If you take a scalar field without radiation, in this case, you can get rid of radiation. So I will take a scalar field, kinetic and potential. You can compute the epsilon parameter. And you can see that the epsilon parameter is inversely proportional to the derivative of f. Then if a fast growing f will produce accelerated expansion. Actually, if it's very fast growing, you will have almost a Sitter period. The nice issue is that, so there is another issue in cosmology, which is the fact that the scalar field typically in GR has to be at least square root of 2 the Planck mass. So it has to have a Transplanckian value. And typically it has also Transplanckian excursion in the field space. So we want to see whether we can get rid of this. And a possibility would be to basically push inflation to the large curvature regime, and then you can easily see from this analysis that in that case you can get rid of this constraint from GR. So this is what I'm running out of time. So basically, we'll take scenarios in which inflation happens at energies that are much larger than the inverse of L star. So let me go fast to the question. So we explore two scenarios. This function looks completely crazy, but I mean, they don't look easy at first sight, but this only has two parameters, which is the scale at which GR is corrected and the scale of inflation. And this case, which is a Gaussian model, it also has the width of the Gaussian, which tells you how fast the function f grows. So let me just show and I'm finishing. I have the conclusion, but I will keep the conclusion for the discussion. So this is, for instance, the function when you put a very large value of gamma. Gamma is the coefficient that tells you how far apart are inflation from corrections to GR, and a value of C, which is lower than 1, in order to have a very thin Gaussian, such that the derivative of f is very large. So if you now see what's the evolution of the cosmology, when you have a value of the scalar field which is sub-Planckian, and actually quite sub-Planckian, you see that you can have quite easily, for instance, in this case, 84 E-folds with almost 0 epsilon. So you have a quasi-de Sitter era, which is long enough to withhold inflation. Notice that, and I'm finishing with this, notice that the quadratic potential is a canonical example of the so-called large field inflation model. And in this case, we realized that higher curvature terms convert large field inflation models into small field inflation models, which opens the Pandora box to explore things as the relation between the least bound and the tensor to scalar ratio and other standard law relations in cosmology that could certainly change in this scenario. I will finish here. I will have the conclusions after this, but I will keep the conclusion for the discussion. So thank you.
Okay, thank you, Jose, for a great talk. Thomas had a question.
Yes, Martin, thank you. But I see another question from the audience by Ignacio Raya, so I'll just wait until the end. So go, Ignacio.
Okay, Ignacio, okay.
Hi, Jose. So I have a question. Isn't
Yes.
there a problem in using conservation of the matter energy momentum tensor in order to obtain the cosmological equation, like the Friedman equation? Because, I mean, this is a higher curvature theory, right? So in general, the notion of conserved energy momentum tensor depends on the equations of motion of the gravity theory that you're using, right? Or I guess it's the point of the fact that in the kind of theories that you're considering, like Einsteinian cubic gravity and generalizations thereof, this is not an issue, right? I mean, this is my question.
Well, I would say that the stress energy tensor has to be conserved. So then this is typically, this eventually may tell you that some terms, you cannot write some equations of motion in the gravity side. And so there, well, if I am understanding correctly, your question is this like in GR, in the first way Einstein wrote the GR equations that were inconsistent with the conservation of the stress energy tensor. But then he found out that there is this extra contribution that gives you the Einstein tensor that makes its conservation automatic. So here I would say that the conservation should be automatic to be consistent with the energy momentum tensor conservation. Anyway, the equation, also the equation, this equation, when I put the scalar field, for instance, is just the equation of motion of the scalar field.
Okay, I see. Okay,
the Klein-Gordon equation. So it's an equation of motion.
Okay, thanks.
Yeah, I don't see any more. Nico has a question as well.
Nico.
So you mentioned an instability with respect to anisotropic perturbations. I didn't understand if it was an instability of this Einsteinian model with respect to anisotropic perturbations. But then the question is, does the inclusion of an inflaton stabilizes that? Do you know that?
Well, the honest answer is I don't know, but certainly if you see the computation of the paper of Starobinsky, certainly it completely changes the computation. So I am not sure. So what I would say is that their computation is not valid for that case. So the solution they found out unstable is the solution H constant for an isotropic perturbation. So even in the radiation case, we don't use the H equals constant solution. So, but in the scalar field, the situation is even much more different than theirs. So I don't see, at least I don't see why their computation should be valid here.
Thanks.
Julio
But certainly this has to be undertook.
Julio has a question.
Hola, Jose. I want to ask you the following, that in order to make everything consistent, you should also introduce higher derivative couplings of the scalar.
Yeah,
So
that's right.
how you think how to construct some of those that could be nice couplings?
So let me, there are many things to say about that. Let me be short. So no, we haven't explored that. This is also an important problem because if eventually there is some possibility to show that any cosmology can be brought to this form through field redefinition, which is a possibility because in the case of the generalized quasi-topological gravities, as you know, the Pablos and some other people, they show that, this will completely make a mess in the matter sector. So it's good at some point to explore a messy matter sector. Now, so we haven't done so, and that's a difficult problem, and I don't know if this is actually doable or not. The comment, another comment that I can make is that in a sense, one can see the scalar field just as a fluid representing the whole matter. So if these kind of terms demand this whole tower of higher spin massive fields, I'm not sure about this, but I would say that possibly the scalar field, the free scalar field, could be simply a sort of fluid resembling the whole contribution of this whole tower of higher spin fields. I mean, the mass scale is roughly the right one, and but this is a hand-waving answer that, of course, would demand hard computation behind to be trusted.
Thank you.
Thomas, I don't know if you want to ask now. Or...
I see more questions from the audience, so I can just wait until the discussion session.
Who has? Yeah, I don't see the hands.
There is Juan and Juan Pedraza and Leopoldo.
Juan Pedraza y Leo.
Okay. Juan, then.
Hi. So this L star that you have is of the. Are you taking it to be the Planck length or?
No, certainly not. No, it's larger than the. I mean, the extreme situation would be L star equals L Planck, but in principle, even in string theory, if this is string theory, L star would be square root of alpha prime. So it's also larger than L Planck.
So it's gonna be like it's the string length, more or less.
Yeah, exactly. If this is string theory, you would expect string length, but yeah.
Don't you get constraints from your paper of graviton scattering?
Well, this is what I mentioned at the beginning. So the constraints are basically tells you that yes. So the quadratic and cubic, there are two answers to that. The quadratic and cubic terms are the only ones that are constrained, but I suspect that this is simply because of our lack of ability to compute all the other terms. In principle, I would expect all of them to be subjected to the same kind of constraints. But this is simply telling you that you have extra fields. So this is what I suggested, that the scalar field, or as you typically do in cosmology, you don't put a whole sequence of fields, but you just simply put matter or radiation representing a fluid of non-relativistic and relativistic constituents. So in that respect, let's say my hand-waving proposal would be that maybe this scalar field is containing the information of all the matter fields in the theory, even if it's string theory or not, in this context, in which you only would expect to have the constituents of matter. You would only expect to separate between relativistic and non-relativistic ones. So this is radiation or matter, basically.
Okay, thanks.
But it's a model, so I don't know.
Okay.
The model could be perfectly could belong to a semblant.
And Leopoldo if you want to ask, we have if you have a short question.
Yeah. Yeah, my question can be short. It depends on the answer. So since we are in phenomenology land, I'm wondering whether you see other areas like black hole, whether black holes are going to be modified substantially, something you can see on LIGO, whether maybe this is galaxy formation or something. Are there other signatures other than cosmology that you can point to, or that you think this might have implications?
Yes, certainly. I mean, but of course you will need, these terms will be relevant whenever you have large curvatures. So it's not plenty of places in the universe in which you have those large curvatures. One possibility would be gravitational waves, but I think the computations are very hard. I don't expect to have progress in that direction. But then also the black holes in these theories behave differently. For instance, they have a sort of REM, so the thermodynamics is such that when you have small black holes, they evaporate very slowly, contrary to the GR case. So this is something that the Pablos did. So I'm telling you about their work. So this, for instance, may be interesting to explore the black holes of these theories in the context of this of the fine-grained entropy that was being discussed in these days quite a lot. And what else? And of course, even in cosmology, one thing that must be done, and we are carrying on it, but I am not sure if we will be successful, is to compute cosmological perturbations, of course, because these all refer to the background of the cosmological space-time, but then you need to check whether perturbations satisfy the constraints posed by the CMB. This is something that is still in front of us, hasn't been solved.
Olivera had the last question.
Yes, hello, hi Jose. My question is also very short and mostly related to black holes. And in fact, you partially replied because to the question of Leopoldo. When at the beginning you told that your criteria is to have a well-defined thermodynamics and mass of the black holes, like criteria to choose the theories. So I wanted to tell if you can precise it, what kind of well-behavior, because I remember even from one of the talks of Pablo Bueno that he was always looking these corrections, like corrections to Einstein-Hilbert. And when you add other corrections, in fact, Einstein-Hilbert has always Schwarzschild-like behavior of the black holes, but when you add other terms, you can completely change fall off and have it falling much slower. And I mean, even, of course, Chern-Simons theories are not included here, but they behave completely differently. But there is the whole spectrum between Chern-Simons and Einstein-Hilbert. So my question is, what kind of asymptotic behavior of this black hole is? Is it like Schwarzschild-like? I think no. Or
the leading behavior is Schwarzschild, but in principle, in Einsteinian cubic gravity, for instance, which is the case that they originally studied, no, you have an extra contribution, which for very small radius, you have an extra contribution like 1/r⁶ or something like that, which is much dominant compared to the behavior of the Schwarzschild solution.
But then what is your criteria? So then it is not well behavior, but something else.
Yeah, no. Well, so the well behavior means to have a Schwarzschild ansatz, meaning GTT times GRR equals one, and then to have, if you to have positive mass, I don't know, positive temperature, but not more than that. So it's quite relaxed well behavior.
Okay, thank you.
Okay, thank you. So hopefully Jose can come to the discussion session and can answer more questions. And then, so we will take a 5-minute break. We'll reconvene 10:50 or whatever time you have. And then Cesar can stay to check for the sharing screen and so on. Okay, thank you, Jose. Then.
Thank you.
Hi, Martin. How are you?
Good, good. So yeah, I'm not the host in principle of in the sense of Zoom. So Elena or Alberto we can check now that you can share screen and everything.
Perfect. Sounds good.
O vamos a hablar en castellano, supongo.
So,
Ya
yeah.
puedes
So should I try?
compartir.
Okay. Hi.
Yeah, try to share and full screen. With Jose, we had a little problem, so just
Okay,
make
okay,
sure.
perfect. I'm just gonna do here. I guess share. Okay, perfect. Let me try. Oh, okay. So now I'm sharing. Is that correct?
Yes, yeah, we can see the,
let me see. When I was going over the presentation here in my desktop, I was having issues in moving forward. Okay, let me see. Yes, I'm doing this. Okay.
That's good. Looks perfect.
Hopefully,
Yeah.
hopefully there won't be issues there. So you see my presentation, okay?
Yes, and we saw going forward with the slides. So.
Okay. Hopefully I won't have the problem this time. Perfect.
Okay, so yes, we have 4 minutes, so I can do whatever. So I will give you a 5-minute warning, and then you have, so it's half an hour, and then 10 minutes for questions that you can also use if you have something, you want to say something at the end, and go a little over time.
Okay, perfect. Thank you.
Okay, so our next speaker is Cesar Aragon from Stony Brook. He's gonna tell us about recent developments in holographic bit threads. So go ahead.
Okay, hi, good morning. First of all, let me thank the organizers for allowing me to speak here and for organizing this nice talk, even though it has to be online. I think we have, or at least I'm enjoying it quite a lot. Today, I would like to talk about some recent developments regarding to holographic bit threads, which is an equivalent way of thinking about the Ryu-Takayanagi formula. This presentation is mainly based on these two papers, one which was published or was submitted recently to the archive. And this work was done in collaboration with Elena Cáceres, Jan de Boer, and Juan Pedraza, two of which are here, and you know very well. So let me just start telling you briefly what am I going to talk about in detail. So first, I'm going to try to convince you that actually this new reformulation of the Ryu-Takayanagi formula is interesting and has mainly some conceptual advantages over the previous one. Second, I will go ahead and tell you how to construct some explicit realizations of the objects that appear in this reformulation. And then I will describe a little bit some dynamical situations, mainly just perturbatively away from stationary situations, and tell you how those, from this perspective, you can see the Einstein's equations and possibly how can you use this as a new way of thinking about ball locality. Okay. First of all, let me start with the Yanagi formula that we are all in love. As you know, this is a very deep formula that connects the entanglement entropy associated to a boundary region. In this case, the boundary here is represented by this line with the geometric quantity, which is just the area of an extremal surface anchored at the boundary of the region in question, of the entanglement region, which is given by this. And this formula basically makes or kind of answer the question of what does the geometry emerges from. Essentially, the answer is that it emerges from some notion of entanglement, from an alternative system, let's say. More explicitly, this formula has also been used to connect the dynamics of entanglement with the dynamics of geometry. So it's not just the geometry in the static sense, but also it's dynamical in its dynamical nature. On the other hand, another feature of the Ryu-Takayanagi formula, the study of this, is that by studying properties of this quantum information quantity, you can also understand or what kind of boundary states may or may not have a holographic dual, a geometric dual. In particular, we know that the entanglement entropy for holographic states obeys some inequalities that are not generally obeyed in any quantum system. However, there are some features that the Ryu-Takayanagi doesn't encapsulate or doesn't answer clearly. For example, one may wonder where or how the bulk encodes the information about the bits that you count when you consider the entanglement entropy, for instance. One such picture you may have, for example, for the case of black hole entropy. So in the case of a black hole, the black hole horizon has some geometric meaning, and then you may imagine, for example, that in that surface, it is the place where the bit threads are stored geometrically. However, this naive interpretation doesn't hold in the case of entanglement entropy, because the entanglement surface is just some imaginary surface. So there is no real intrinsic geometric meaning into the location of the minimal surface. To make this point even more clear, let's just consider the situation in which the minimal surface jump, which is actually generically when you consider these joint regions. If we change the relative distance between the regions, then we have a discontinuous jump. And so if we associate some kind of physical meaning to the location of the minimal surface, then it seems odd that the bits, if we say that the bits somehow are encoded in this place, then it seems odd that those bits jump across phase transitions. Before proceeding, since this is a little bit strange, let me just, are you hearing me clearly?
Yes, yes.
Okay, perfect, thank you. So this discontinuity in the minimal surface puzzled some issues, but more explicitly also the definition of the entanglement entropy, the connection of the entanglement entropy with areas, or more clear, or more specifically, for example, properties such as subadditivity, monogamy, or even the mutual information itself, seems a little bit obscure from the perspective of the Ryuta-Kayanagi. It's just obtained by, it's just some formal properties associated to extremal surfaces that crosses different regions in the bulk geometry. So it's a little bit counterintuitive. So precisely based on this kind of conceptual issues is that Hedrick and Friedman propose a new formulation that essentially, or a conceptual way of thinking about Ryuta-Kayanagi that solves some of these conceptual issues and actually gives a nice interpretation of how the bulk, to the answer of how the bulk encodes the entanglement entropy. Such formulation is then given in terms of a flow maximization. So for that, we need to introduce an object. That object is the flow, which is a divergentless vector field, which is norm bounded from above by the Planck scale in the problem, like 1/4 G-Newton. And so the statement, the main statement is that you can compute the entanglement entropy with this auxiliary object that maximizing in the space of all divergentless vector field, which are norm bounded, and the maxima of this flux will give you the entanglement. Essentially, the equivalence between these two is just an example of max flow mean cat equivalence, which can be seen intuitively in this picture. So for example, in this case, we are just having like the boundary, we are thinking of these 3 circles. The region that we are interested in is the circle. And then we maximize the number, the flux that from the circle A to its complement. And then the maxima will hit first precisely in the region in which the cross section is the minimal possible. So this is pretty intuitive. And right there is precisely the place where the norm bound constraint will hit first. And in that case, we know that the vector field has to be orthogonal to the cross section and will have to be 1/4 G-Newton, and then that means that the flux will coincide with the area in that case. So essentially, this statement, which is actually non-trivial to prove in full generality, essentially just tells you that there are no obstructions to increasing the flux other than the one presented by the minimal cross section or the minimal area. Now, going back to the physical interpretation, the term threads that I'm going to use also as vector fields, flows, or threads, it just refers us to the integral curves of these vector fields. But it's also convenient to think of those as actual macroscopic objects or of finite thickness, essentially like a tube of finite thickness, which counts like or propagates the information of the bits in the boundary theory. Essentially, this is like so the threads are responsible of the entropy between, or it's like a bulk representation of EPR pairs that computes the entropy between A and its complement. And so this is a very nice geometric picture of how the bulk encodes the entropy. Okay, this is just a different picture. Finally, let me just mention that this conceptual way of thinking about Ryuta-Kayanagi also gives an intuitive answer of why the entropy, generically, the entropy or entropy of objects in gravity scales as area instead of volume, essentially is because the entropy is encoded by these one-dimensional objects. And so it must scale as the area. Now, it turns out that this is just a explicit illustration of how a thread configuration will look like. In particular, this shows you why you can compute the entropy just by counting threads that for a particular max flow situation. I will go through this later on in more detail. The point here is just to illustrate how across a phase transition you can, even though the minimal surface can jump from being the disconnected one to being the connected one, which will be all these 2 semicircles, with the threads you can still have a continuous transition across that. So this also will solve the issue about this continuous jump. Okay, finally, let me mention that most of the work in the previous year that has been developed in the context of this max flow problem, it has been done in the context of a complex optimization framework. Essentially, the point is that this max flow prescription that I told you, it turns out to be a case of a complex optimization program, and therefore you can use a bunch of techniques that appear in that framework. So just to mention a couple of those techniques is the one known as complex relaxation, Lagrange duality, and so on. And so in this direction, then there has been a lot of interesting results. For example, it has been you can prove without using all the machinery of differential geometry this max flow mean cat property, but as well, but also some other properties of these max flows that I'm just describing for you today. Similarly, in this paper, there is there was discovered and proved this property that I will mention briefly, which is called multi-commodity flow or max multiflows. And there was also developed a flow maximization problem for the case of higher curvature theories of gravities and so on. I myself have some little work in this context in which we describe what will be the max flow problem, which will be dual to a membrane theory, which is essentially an effective theory that describes the entanglement entropy for large regions. Okay, but today I'm going to talk about a different perspective or a different approach to studying bit threats. And that approach will be to study explicit realizations of bit threats. So most of the previous work has been done in a very abstract way, or let's say slightly mathematical way. So here we would like to do to try to make progress by understanding how to build explicit instantiations of such max flows. In particular, the hope is that one might be able to see new properties that these flows has to satisfy in order, for example, to prove the higher entropy inequalities. This hasn't been done so far, at least in the language of max flows. And also there might be ways to, or the gravity might inform us about what natural candidates for flows have more physical meaning than others. And such candidates may help us to understand dynamics and so on. Once again, this is just the summary of that I did at the beginning. So I'm just gonna proceed and start with the static situations. I'm gonna study dynamics next. So first, let me just start by describing two methods for constructing threat configurations and with some generality. So the first method is what we call a method based on integral curves. So essentially the method or the proposal is that we start by making a proposal of alternate or of possible integral curves for a max flow, which need to satisfy certain conditions. Of course, these integral curves should not intersect at any point. And in particular, at the minimal surface, they should intersect the minimal surface orthogonally, because we know that at the minimal surface, which is the bottleneck, then the vector field should be normally and the magnitude should be saturated. So we put this boundary condition here. So for example, here I illustrate a section of the minimal surface, then the thread should intersect normally and the magnitude of B should be 1. And then by imposing the flux conservation of flux, which is just an integral version of the divergence condition, then we can determine the norm of the vector field everywhere along the thread or along the integral curve just by imposing this condition. Essentially, you can write down a closed formula for the norm of the vector field, and then one need to check afterwards or a posteriori whether actually the norm bound is obeyed everywhere else given this construction. So I will give you some examples. So for example, if we consider a sphere, the minimal surface will be a hemisphere. And if we propose as the integral curves of this vector field to be geodesics, then this geodesics, of course, should intersect normally. At the minimal surface, it should be equal to 1 there. And then by imposing the divergence constraint in the way I explained to you, then you can find these nice plots for the magnitudes of these vector fields, which satisfies all the conditions. Therefore, there is no violation of norm everywhere. Indeed, this construction is in some sense optimal because due to the fact that we use geodesics, the distance between threads is as large as possible. And therefore the magnitude of B actually decreases as fast as you get away from the minimal surface. As we will see later on, this feature, it will be convenient for studying perturbations. This is just another example. Here, just for strips, you can do something similar. In that case, the more natural choice of integral curves will be integral curves that look like the minimal surface itself. And you can do the same prescription and you find these nice plots for various numbers of dimensions. Let me just mention once again that for the spheres, in the case of geodesics, you can even write down a closed expression for the vector field and its magnitude, which we'll use later. Okay, so far I have described one method for constructing max flows, which depends how efficient or how convenient is that method depends on the geometry in question. Sorry, I didn't mention, but all these geometries that I'm describing at this point is just for pure ADS, but of course it can be applied also for the presence of black holes and so on. Okay, an alternative, what I would say, which is like a dual description, a dual prescription, will be to use instead a level set functions. So level set functions is just to propose a set of surfaces which corresponds to the surfaces of constant values of the flow. So the vector field B is constant across all these surfaces. So for example, here I give you some example. And then a condition of that set of level set surfaces is that, of course, it should contain the minimal surface as one of those, as one of the set. And then there, at the minimal surface, we know what should happen. The magnitude of the vector field should be equal to 1. So in equations, basically, the proposal is that I said that the vector field with index down should be equal to some function multiplying the derivative of the function phi, which describes the level sets. It's the scalar field that describes the level sets. And so we impose this boundary condition at the minimal surface should be saturate the bound. And then by solving the divergence condition, we find the value of the function phi everywhere else. So once again, we impose the boundary condition of phi at the minimal surface and solves everywhere else. And indeed, if we take as the level sets just this sphere-like surfaces, then we go back and find exactly the same kind of thread configuration. But of course, these two methods, the method that I just described now and the previous one, are completely independent and can be used actually efficiently for different tasks, as I'm going to proceed now. Okay, so let me now move. I don't know if there. Okay, sorry. Let me now move to describe two fundamental properties of these max flows that would allow us to prove things such as subadditivity, strong subadditivity, and monogamy of mutual information. These are the so-called nesting and max multiflow. But let me describe them in detail through an example. So the nesting property is the statement that there exist thread configurations that maximizes the flux of any nested set of regions. So just to illustrate the problem, let's assume that we have the region A, which is inside the region B. And so this property will tell you that you should be able to construct a thread configuration such that the flux through A, or equivalently to M of A, is equal to the flux through M of B. Since these regions are nested, that should be possible. And in this picture, I show you exactly how to do such construction. So, and the construction is the following. I'm going to do the construction by using the level set method, and I'm going to propose that the level set functions corresponds to minimal surfaces themselves. If I do this, so these dotted points are just minimal surfaces that interpolate between A and B, a property of the due to some properties of the minimal surfaces, and then what was going to happen is that if the vector field B is 1 at M of A, then the vector field will also be 1 everywhere else. So when we impose the divergence condition, that's what we get. And so the threads, which are the vector field, which are orthogonal to all this set of level set surfaces, will have magnitude 1. And so it will generate for us a highly efficient thread configuration. It's actually what the people call maximally packed flows. It's a thread that is as tightly packed as possible, given the conditions. And of course, by construction, then if I compute the flux through M of A, I will get the area. And if I compute the flux through M of B, I will get the area. And therefore, this construction will realize explicitly this nesting property. Okay, so now let me show you another interesting property of this max flows, which is called max multiflow. And this is highly non-trivial and it's extremely useful. So let me see if I can do it efficiently. So the idea is that, again, and now the boundary geometry here is this line and the bulk is everything else. And so the idea is that given this boundary, this Riemannian manifold with boundary, then if I partition the boundary in a given set of boundary regions, in this case I choose A, B, C, and D regions, then the statement is that there always exists a thread configuration that computes for us the entropy of each individual region just by counting threads. In this case, I'm forgetting about the direction of the vector field. So, so what I do is to maximize the number of threads that connect the region A and everything else as the entropy of A. This just by definition. And so what I found here is explicit realization of that statement for the case of 4 regions. And the way we construct this example is precisely using these level set methods with minimal surface. So all these threads are tightly packed and are connecting the region M of A with the M of D. This is the minimal surface associated to the region D, and so on. So just by using by using families of nested minimal surfaces, we can construct all these tightly packed threads, which realizes this theorem. So this is the application of our construction. This is one of the interesting applications, and to show how this property proves the properties like monogamy of mutual information and selectivity. Let me just do this counting exercise. So as I said, the entanglement entropy in terms of threads is just the maximum number of threads that connect these two regions. For example, the subadditivity, which is the positivity of the mutual information, since for any such, if I use the previous theorem for number of regions equal to 3, A, B, C, and use this property, then I know for sure that the entropy of A is just the sum of these two numbers, the number of threads connecting A with everything else, A and B and A and C, and so on. And just by writing the definition of the mutual information, I find that this is equal to 2 times the number of threads connecting the regions. So this is somehow like, this also gives you some nice interpretation of the mutual information. It's just the number of threads that in this particular setups connect the regions of interest. And of course, it's positive because this number is a positive number. Similarly, one can do for monogamy. The monogamy of mutual information just comes from for such particular construction, the construction like this one, in which we use 4 regions, and then we maximize the number of threads connecting all the regions in this way. Then just by, one can write the entropy of each individual region as a sum of threads connecting different parts of the boundary. And so if we do that, then we immediately get some inequalities. Essentially, the entropy of any joint region will be bounded from below by the number of threads connecting those regions. We immediately, by doing combinations of these inequalities, we get the monogamy of mutual information. So this is just tells you how the threads encode these non-trivial properties about entanglement. Okay, so this is all I wanted to say about these static situations in which the original proposal by Friedman and Hedrick applies immediately. And now I would like to study a little bit of dynamics also in this spirit. So for dynamics, of course, we need to use instead the Huveni, Rangamani, and Takayanagi prescription. And Hedrick and Huveni has been promising already for quite some years that they have a covariant formulation of this problem. However, we can still study situations without using this covariant formulation by using the maximum, which is just an equivalent version of the HRT formula. This is just in detail what the HRT formula says. In that case, we choose just codimension 2 surfaces, which are extrema, anchor at the boundary of the region, and then we minimize over all these extrema. The maximum prescription uses instead, or what it does is basically extend the Ryu-Takayanagi formula, but now includes variations over the hypersurface sigma, which is a space-like hypersurface that contains the boundary of the entanglement region. And so for every sigma, we minimize the area and then we maximize over all choices of sigma. Therefore, one can just, by using the Friedman-Hedrick prescription, we can write a max flow version, which is exactly the same. Now we change the minimization part by a maximization of a flow. However, interestingly, if we are just interested in a small, in dynamical situations which depart from a static one, just by a small perturbation, then we can always use just the sigma that appears for the static, for the unperturbed situation, as one of the maximizing sigmas, let's say. And so we can simply use the original max flow version, but only by choosing any sigma which is perturbatively close to the original one, provided the perturbation is small. And then at first order, everything is okay. So this is precisely the formula that we're going to use, just the same formula, but for sigma naught, which is the unperturbed sigma. Okay, so in this case, then we go to, we study perturbations in Pfefferman-Graham coordinates in which the metric adopts this form. We know that the asymptotic form of the metric will describe the expectation value of the energy momentum tensor in the state, which is dual to this perturbed geometry. This is given by this, where this is just a way of writing the perturbation in this gauge. And so we can use the 2 methods that I just described before to understand how the threads, how the perturbed threads will depend on the metric. But what we can see without doing this explicitly, immediately, due to the way in which we constructed these objects, is that the vector field encodes the information about the dynamics or the information about the perturbation of the metric in a highly non-local way. The reason for that is that the way we constructed the magnitude of the vector field was
5-minute warning.
Okay, thank you. Was by imposing the divergenceless condition. And this divergence condition basically comes as an integral. And the integral depends on the value at the minimal surface. So essentially, the vector field everywhere else will depend on the value of B at the minimal surface and the metric there. And therefore, that introduces, or that tells you that the way in which the vector field encodes the information of the metric is highly non-local. Therefore, there is not much hope in using these methods that I described before into understanding the dynamics of the metric. So this point, but additionally, there is another point in these constructions, and is the fact that if I use the flow formula in the way that I described for you, it turns out that the definition of the flow itself depends on the metric. And so since I'm varying the metric, it seems that the problem is highly nonlinear in that respect. It turns out that there is actually an alternative way of thinking about this problem, which turns out to be quite useful. Oh, I got again this problem of, oh, I don't know. Sorry. Let me do it again. Sorry. It just doesn't, okay. Sorry, yes. So, and it turns out that there is an equivalent description in terms of differential forms. And in terms of differential forms, then the dependence on the metric only comes through the norm-bound constraint. So the formula is the following. Now we also need to maximize the flux. Now it's described by this D-1 form, which need to be closed. So the divergenceless condition is equivalent to the closeness condition here. And the closeness condition doesn't depend on the metric. So in that sense, it's metric independent. However, we'll still need to worry about the norm-bound constraint. The norm-bound constraint seems particularly complicated in this language. Now, the map between this formulation and the previous formulation in terms of vector fields is very straightforward. It requires the Hodge dual of the form, which construct the form of the dimensional one form, and then you just convert it into a vector field. Here is the connection between the closeness and divergenceless condition. And when we evaluate omega in any surface homologous to A, then this is related to the normal component of the vector field. Epsilon and epsilon tilde are just the natural induced volume forms in those surfaces. Okay, so and then going back to the perturbative dynamical situation that we want to study with the bit threads, then let me just review what are the kind of properties that the perturbation of the form would need to satisfy. So in particular, the closeness condition of the full form, the perturbed form, it reduces to the closeness condition of this perturbation, which is nice. So the perturbation itself needs to be close. The boundary condition, the fact that at the minimal surface, the form needs to coincide with the area, then means that the perturbation itself at the minimal surface should be related to the change in the induced area due to the metric, which is also a nice local condition. Similarly, the norm-bound constraint, you can write explicitly what does it mean in terms of these inner products, but that's not going to be super important. Of course, all these properties we want to satisfy. Now, what are the kind of geometries for which we can hope to get as much information as possible? Of course, that case is the case of spheres, because in any CFT, we know how is the molar Hamiltonian, and we have this nice connection between entanglement entropy and entropy via thanks to Cassini, Werth, and Myers, in which we know what is the killing vector which asymptotes to the molar flow in the boundary theory. And given this killing vector, then we can also associate a conserved quantity. And then using the framework of Ayer and Wall, then there is this very interesting paper that uses this D-1 form that is constructed just from gravity consideration, which is essentially the conserved quantity associated to this killing vector. And then we can connect this with the Einstein's equations, essentially. So the idea is that Ayer-Wall gives us an explicit expression for a form in terms of this codimension 2 volume form, such that when I integrate over the minimal surface, I get the change in the area, which via Ryuta-Kalyanaki is equal to the change in the entanglement entropy. When I integrate over the boundary region, I get the change in the expectation value of the molar Hamiltonian. Its external derivative is proportional to the linearized Einstein's equations. And so by integrating over sigma A this form, then we get this nice relation, which essentially says that if this equation is true for any boundary region, then what we conclude is that provided the first law of entanglement entropy, which basically is the equality between the first variation of the entanglement entropy and the variation of the expectation value of the Moeller Hamiltonian, then the Einstein's equation must hold in the bulk. So this is, in 2 words, the content of this very nice paper by Faulkner, Giga, and so on, etc. So our proposal then for these bit threads is that we can actually use the IR-wall constructions of our perturbed bit threads. And in that case, I write down explicitly how this formula looks like. Everything works like we get this nice connection between the closeness condition of the perturbation with the linearized Einstein's equations. It turns out that if we choose the form to be the geodesic form, then we immediately get the norm-bound constraint satisfied, at least up to first order in the perturbation. And additionally, we get this nice boundary condition of the form, which locally it will look like the integrand of the Moeller Hamiltonian. So we get this very nice construction coming from the IR-wall formulation that satisfies all the properties, and so it seems to have a crucial role in this holographic interpretation. Now, just to finish, let me just tell you that provided you impose sufficiently strong conditions on this form, then it seems that, this construction will also give us a way of thinking about bulk reconstruction. As you can see here, the form is linear, is just a linear operator acting over the perturbed geometry. So we could write it in this way. So we have this, when we translate it into a covector, then we have that the perturbation of the form is just some linear functional acting over the perturbed metric. And then that suggests that if we took this as our input data, or as fundamental variables, then you could construct also the metric from these threads. And the reconstruction, we actually work it out in the paper I mentioned, in d=2 and d=3 explicitly. For higher dimensions, you need to include more forms. So this is the index here. And I just want to finish with a particular formula, just so that you know more or less how this inversion formulas looks like. So this is the trace of the perturbation in terms of the form. Okay, so, and there are many future directions, and this is basically the content. So thank you very much.
Okay, thank you for a very nice talk. And we have questions. So first, Ricardo Espíndola.
Yeah, thanks for the nice talk, Cesar. My question is, so based on this nested property of the bit thread, it seems that maybe it's possible to compute lengths of curves in the bulk, do this bulk reconstruction. And if that's possible, then maybe you can define points of bulk, families of bulk points. But it seems that one obstruction is that this integral curve prescription will say that this vector field will be like divergent at that particular point in the bulk. Can you comment if that's possible? Or maybe?
Well, why would you say that is divergent? Sorry.
Because it is a point in the bulk and you are defining a vector field there, right? It is like a derivative that is not well defined at a point.
Okay, I guess. I mean, I would just think about like the area in the limit in which the surface goes to a point. I guess that limit might lead to something well defined.
Yeah, that's connected with my previous question. Like, if there is it's possible to reconstruct in the bulk.
So I guess the answer is that you will not be able to do that with a single vector field, with a single flaw. So this nesting property only works for boundary regions, not for bulk regions. And second, you could reconstruct surfaces. I think this just by using the same prescriptions in the usual Ryu-Takayanagi formula. But similarly, that it happens in the Ryu-Takayanagi formula, you need not just the entanglement of some region, but some linear combinations of entanglements of regions. So I think in that case, what you will need is to consider a family of thread configurations. Use you do some arithmetic with that, like add flows, subtract flows, and so on, and then you might be able to write an explicit formula which computes this area as a flux. Yeah, I think that's possible. And in that case, probably you need to also remove some part of the bulk so that you don't get this kind of divergence like that you are mentioning. So basically, it would be like to consider this surface, or an alternative way of looking at it is just to consider these surfaces as part of the boundary, let's say. You can just consider the surface that you want to describe as part of some imaginary boundary and try to define flaws to compute that. So we haven't done explicitly, but I think Juan was interested in exploring that question.
Would be nice to try. I think it's possible.
Yeah, I think so.
And also another more basic question is it possible to give a bit rate geometrization of the quantum correction to the RT surface? You know, the Faulkner-Lefkowitz-Maltasena equation.
Yeah. This is another line of research that we are pursuing currently, and I think the best scenario or the best context in which that could be possible, at least in principle, is in this case of double holography geometries, because it's like purely geometric. So I think the intuition is that generically you do not expect to have a geometrization for bulk entanglement, but in the cases in which the bulk entanglement can be computed holographically via some minimal surfaces in a higher dimensional space-time, then in that case, then you can think of threads living in this higher dimensional space-time, and then just project that out into the lower dimensional expansion context. So this projection thing, the thing that will somehow compute these quantum corrections. So I think the answer is yes, but it will not work in general, because it's similar like to the statement that not all quantum states have a geometric dual. So it will just be for some particular bulk quantum states which has some kind of geometrization. And those, I think, we might hope to be able to describe them in this double holographic context. So that's one direction that I'm also interested in.
Nice. So I don't know if there's
David,
time for a final question or comment.
Okay. Let me ask my question. To what extent are these bit threads actually unique? I mean, if we're going to assign them a physical value, there needs to be some uniqueness to them. Otherwise, what is the gauge freedom that's in there?
Yes, there is a lot of freedom. The thread is actually highly unconstrained. The only place in which there are somehow constraints are the bottlenecks, in which this has to saturate the norm bounds. But outside this bottleneck, they are completely unconstrained. And somehow this freedom, we are kind of happy with that, because this is just like every configuration of threads somehow might tell you about some possible microscopic state which has the same entanglement entropy between A and A bar, let's say, which geometrically, yes. So this will be like some naive interpretation, at least provided that this microstate can be described as a bunch of EPR pairs, like the entanglement is just by law. It's given by.
Yeah, I'm just more concerned about how would you actually measure the bit threads if they're not physical. So it's. I mean, when you say give us this data, this is not kind of something that I would know how to measure.
Yeah, we cannot measure. I mean, the thing that you can measure are just the fluxes that I'm telling you about. The fluxes are the things that are physical, and what I'm saying is that it's similar to the fact that you have this macroscopic thing, which are the flux or the entropy, but then there are a lot of microscopic configurations that give rise to the same entropy, and then somehow you can associate this huge amount of freedom with the freedom that you have in moving the threads around and having any kind of configuration in the bulk. So the threads are not physical, I agree. But then what I'm just trying to say is that we don't know if there are some special thread configurations that have some physical meaning. We do not know that. And so kind of the hope of this bulk reconstruction is that maybe if you impose sufficiently constraining properties to those threads, like bulk locality and so on, you might be able to actually single out some canonical thread configuration. And then use those canonical configurations for some sort of things. Like, for example, in this case, I more or less very quickly mentioned how one could use such a canonical thread to do bulk reconstruction. But that would require a lot of extra input. Like from the definitions, from the formulas, there is no input that single out a particular thread configuration.
Thank you.
Sure.
Carlos has a last question.
Okay, Cesar, thanks very much for the talk. I find the topic very interesting, but I understand very little. So the last question might be very simple-minded. And so suppose that you do the following two experiments with these threads, just maybe in the direction of what David was just asking, to get a bit more of their physics, try to see what they are doing, right? So suppose in the first experiment you do is putting a singularity in your space. And do you have any intuition of what these threads are going to be doing in that case? And the other case, let me ask both in one, and then you tell whichever you wish. In the case of field theories that are confining, one can see that the entanglement entropy shows a first order phase transition. Is it more or less intuitive what these threads are going to be doing in that case?
Okay.
You answer whichever you want, and if not, we move into the discussion session.
Okay, no, that's good. I think, I mean, singularities, I don't think it will affect per se the threads, because as I said, the threads, since they are so floppiness, so floppy, they can be anywhere. So provide, as far as though that singularity is not, let's say, close to the bottleneck, then it will not really affect much the thread. The thread will just avoid the singularity very easily.
Couldn't one think that, as it happens, that the singularity will be such that it will attract the Ryuta-Kayanagi surface, right? The Ryuta-Kayanagi surface will want to fall there.
Yeah, if that's the case, or at least for some surfaces, I guess. No, the singularity will start to play a role as provided the surface is sufficiently large, I guess.
Agree. Yeah.
I guess. And then in that case, if of course, then I think that would be interesting to see what kind of constraints will that impose to the thread, so that would be like to thinking about the Maxwell-Minket theorem in cases of some kind of exotic geometries in which you have some weird things happening. As far as I understand, the equivalence between Maxwell-Minket was proven full generality without even without referring to any specificities of the background. But maybe one condition that is just assume is that is smooth and it's well behaved. So maybe there could be some issues even with the statement of Maxwell-Minket in the presence of singularities. So I agree that may actually be that there might be something in that point. What was the other question?
If you want, we leave it for the discussion.
Yes.
We leave it.
Yeah, so there was a last question also by Ricardo that I sort of cut off, and Julio Virrueta has a question, but let's leave it for the discussion. So thank you, Cesar, for a great talk, and we take 5-minute break, so or maybe 3 minutes, we come back 11:35, and Maria maybe can start sharing the screen and checking that everything get done.
Thank you. Thank you. Bye.
Bye. Maria, you are muted, so if you can.
Yes, hi, how are
¿Qué
you?
tal? ¿Cómo andas?
So let's see if this works.
Yeah, we can see yeah, that's perfect.
Yes, do you hear me?
Yes. So we
Okay.
have a couple of minutes break, so if you want to do something and then come back.
Sounds good. I will mute
Everything looks good.
myself and then read.
You are in the office, or?
Yes, I'm in the office.
Oh, they let you go. That's good.
I sneaked in. I'm the only one here.
Okay. So we'll tell you 5 minutes before. So you have half an hour plus 10 minutes. So before the 5 minutes before the half hour, I tell you 5-minute break. And after the half hour, 10 minutes is for questions, but you can also use it for if you need to finish. I mean, you can go over time a little bit.
Sounds great, Martin.
Yeah. Okay, so I think we can start. So the next talk is Maria Rodriguez from Utah State and Madrid, and she's going to talk about electromagnetic energy extraction from rotating black holes in ADS. So
Okay.
go ahead.
Perfect, thank you. Can you hear me well, Martin?
Yes, it's
Yes,
perfect.
okay.
Yeah, no
So
problem.
before starting, I wanted to thank the organizers, Tomas and Elena and Mariano and Alberto, for organizing this workshop. It's very interesting to see that there's so many participants and friends from old times and new times. So I appreciate that you invited me to give a talk, so thanks. So as you can read here, I will be discussing some ideas about electromagnetic energy extraction. And in particular, I will be discussing this process for rotating black holes in ADS. So the three pictures that you see here are the first picture more related to the astrophysics image. This is a real image of energy extraction from what we think is a black hole here in the center, and you see some black hole jets. And then these two pictures here, that is what I want to discuss and show you in more detail, which is the energy extraction process in a BTC black hole, so in ADS3. And on the right-hand side, the similar model for energy extraction through electromagnetic fields from the near horizon region of a Kerr black hole in ADS4. And this is what I wanted to discuss today. So, oops, I'm not sure if this is, oh, okay. So the idea is then to present some of these new electromagnetic energy extraction solutions from black holes in ADS. And basically the aim was to show the applicability of these electromagnetic energy extraction models in ADS. That was the first step. And the idea was way, far away currently on the horizon. The idea was to find some insights into holography jewels for these models. And so we'll be focusing mostly in ADS3 and ADS4. And what I'm going to be presenting today is work I did in collaboration more on the ADS3 side in BTC with Ted Jacobson a couple of years ago, and then more recently with Nele Kalebout, postdoc, and Herman Belinde at Princeton. So let me give a brief introduction. Probably you know about what these energy extractions models are, but the ones that involve fields are perhaps a little bit more not so common to study, say, in a common GR course. So we all know this energy extraction mechanisms when there's a black hole that contains an event horizon that I will paint them here in blue. And those black holes contain some ergospheres, so they're rotating black holes. And so if we send a mass particle into the region close to the black hole, it will go through the ergosphere. And if within that region here, painted in red, and what I'm doing here is there's an axis symmetry here where you should be rotating this around. So if we are within that kind of donut-shaped region, which is the ergo region, and you split the particles into B and C, one particle would go into the black hole and the other one would fly away in some sense. And that energy of the particle that is flying away has a larger energy than the original particle without the split. So in the end, if we look at this, and this is the Penrose process basically, is that we observe a positive energy flow and some that flows away from the black hole, and some energy that is negative that flows into the black hole. Okay, so there's energy that we can extract basically from the black hole through this process. Now, there's another process in which we can also extract energy from the black hole, which is the one that I'm going to be discussing today. That is one in which the black hole is going to be rotating, but is going to be threaded by a magnetic field or an electromagnetic field. And that electromagnetic field in the background of this black hole will also have another type of Penrose process. It would be a massless field, but it will still thread the black hole and extract energy from it. And so Blanford and Znayak looked at this process in the 70s for black holes. That's where the name of these models came originally, from adapting electromagnetic fields in backgrounds of stars to black holes. And they showed that what happens is that the field lines that you see here, once they go in the region close to the black hole, they actually start twisting around. And so energy can be extracted within this closed region only with electromagnetic fields. And so charged particles would feel that a background electromagnetic field and are going to be able to escape from falling into the black hole. So this is the Blanford-Znayak process, which is very well known in astrophysics mostly. It requires a few elements for the black holes. So as in the Penrose process with matter, it will need an ergosphere. And so within that region, the magnetosphere, so the electromagnetic field in that region rotates with the black hole, and so it will be able to extract energy and also angular momentum from the black hole. And we will talk more about this combination of elements of energy and rotational energy that can be extracted. So that is the models that we are going to be focusing on, but the original idea from this is trying to emulate the processes that we see actually in black holes in the sky. So these objects, the black holes, do have some collimated jets that come from, at least this is what observations show us, and also from the ones that you probably saw from M87. They show that there are jets of energy that are coming out from a central point here, and those are those jets or quasars that we see that this black holes power. So these are the biggest energies after the Big Bang that we have been able to measure, these black hole jets. So these energies are modeled in a very sophisticated way with magnetohydrodynamics currently in numerical relativity. And they do play a very important role, in particular this BZ model or the Blanford-Nyack model for this mechanism to be present and in how to model this black holes with the jets now. And so it's still, even though, you know, there's 40 years of investigations of this problems and models, it's still a challenge to understand very well how the electromagnetic energy organizes in the space close to the black hole. And the intention of trying to extend these models to extremal situations, meaning cases of highly rotating black holes, or now in these generalizations of the models into ADS, is trying to see also the limitations of these processes or models in the solutions that we know about, that we know currently for rotating black holes. So the mechanism is described, so in my very minimalistic pictures, they're described basically by equations that are these ones here. So they're not very complicated equations, you don't know those. So on the one hand, you have Maxwell's equations. So in the background, so in curved backgrounds where you have your black hole lying behind this, and there's an electromagnetic field that generates a current. And in the models, and that we also think emulate what happens close to some of the black holes at least, there's an additional constraint equation that constrains the current generated by this electromagnetic field in this way. And this condition is called the force-free electrodynamic condition, or force-free electrodynamics. And we will see briefly how this comes out. So basically, these are the equations that we need to solve for this process of energy extraction, and then compute whether this solution does indeed extract energy from the black hole or not. So we can represent the electromagnetic field and some additional matter through the stress energy tensor. And we know that this quantity is conserved. Now, in this approximation, where we first have a current that's being generated by this field, we know that the stress energy tensor for the electromagnetic portion of the stress tensor is really not conserved in general. But within the approximation of this force-free approximation, what happens is basically that we can ignore the interaction of matter, and the most relevant contribution to the process comes mostly from the electromagnetic field. So what it actually is conserved is the stress energy tensor that is generated by this electromagnetic field. And so this basically gives this Lorentz force density to be equal to 0. And that's where we take this a name of force-free condition that we will have to solve in addition to Maxwell's equations. So these are the equations that we are going to use. And so what I'm going to briefly mention here, again with basically pictures, is what are the solutions that we currently know. So the solutions that we know in asymptotically flat black holes, and mostly all the investigations have been done for the Kerr black hole, are perturbative solutions. In terms of the analytical solutions. That is originally what was done in the paper by Blanford-Nyack, and then throughout the years there have been new solutions that appeared. So basically one starts with a Schwarzschild black hole, and one can find a solution for a field that, here you see the field lines, and in the center you will have the black holes, and this is the equators. So the field lines can be vertical, they can be radial, as if there was a monopole in the center, more parabolic or hyperbolic. And then what one does is one looks at a small rotational parameter to see how the solutions or solutions to this very nonlinear system constrained equations can be found. And this is what we know analytically. There are other ways of solving the equations, and this comes from a very robust field in numerical relativity, where this involves relativistic magnetohydrodynamics. And what you see here is a black hole that is threaded again by some electromagnetic field lines that twist around in closer regions and collimated or centered through the poles of the black hole in opposite directions. So then there were some studies into what happens with these fields in the extremal rotating black hole case for Kerr. And we have looked at also the near horizon extremal Kerr solutions, and we found not just a few solutions like the ones I'm showing you here, but we found many towers of solutions for this model, for the force-free model in the near horizon extremal Kerr black holes. So this is mostly what has been done in a very short presentation of these models and background. Now the question is, what happens with this Bamford-Znaeck models, or force-free electrodynamics or energy extraction through electromagnetic fields from black holes in ADS? Well, when we started thinking about this with some of my collaborators, we found in the literature some papers that were signaling that there were a few solutions that one could build, but none of them were energy extracting. So that was the question: do these models? So can we find solutions that actually in ADS rotating black holes that are doing the same as the asymptotically flat ones that are extracting energy? And so what we started doing was to look first in 3 dimensions. And so what we wanted to look at was into BTC black hole that has everything we needed, which was a horizon and every region. So could we solve the same equations for BTC in 3 dimensions? And maybe then if we have the exact solutions, analytical solutions, we could look into the holographic duals of these solutions. And this is what I did with Ted a couple of years ago. And so we built a toy model, meaning that we were looking at not the astrophysical idea of looking into these models in 2+1 dimensions now. And well, we tried to find some ideas of the simplified model for the BTC black hole mostly. To our surprise, what happened is, as I will briefly now show you, we found the electromagnetic version of this process in ADS, but we didn't really need a plasma. And that was a plasma-less model. So a very similar model that will extract energy in ADS 3, but will not need the plasma, meaning the current will have no contribution, and the field itself will be able to just extract energy from the black hole in the center. So what we started doing, because the problem we thought was going to be very easy since it's BTC in 3 dimensions, well, it ended up being a nightmare project. So we thought perhaps we would look into the 4-dimensional case. So we started with the black string, basically, which is the geometry that you see here, And so what you see is the first three would represent the black hole, and then some additional a line that we called, or direction Z. And what we did was to build a solution that contained a generic form with a horizon and some rotation in it for the geometry, and some additional conditions to have or guarantee that the solutions have an ergosphere. So we found solutions, analytical solutions that are of this form. So this is the field strength for the solutions that we looked up. As you can see, there's an eye here that will represent the current, the magnetic current. This here will be the magnetic flux. And in addition, what you find is that the electromagnetic field lines do have also an angular velocity. And so this is omega f, not to be confused with the omega h, or the angular velocity for the black hole itself. So this is the solution for this form of black string that is energy extracting. And we imposed a few constraints. So it should be stationary and axisymmetric. And we could as well find the dual of the field in this way for this. Now, what we did was to find the reduced case, which we also found that that exact solution was the solution to the BTC black hole if we place the 3D metric exactly that corresponds to the BTC black hole. And to our surprise, so this is how the square of that field strength is, which is positive. To our surprise, the solution did not have any plasma, so it did not generate a J current, and the constraint was satisfied. But there was energy flux that was being extracted, or non-trivial energy flux through the horizon, which is this combination here of the difference between the angular velocity of the black hole's horizon and the the angular velocity of the electromagnetic field and the magnetic flux, in the same way as the power formula comes out in the Kerr black hole in flat space-time. So the field lines, and here this is a crosscut. So this is in the two-dimensional direction. So basically this point in the center is the singularity through at the center of the black hole. And here I'm representing the different regions. So the gray is the inner horizon for the BTC black hole. In purple, you see the event horizon, and this is the ergosphere. So you see the field lines that can escape through these different regions. Here there are different values for the parameters, this omega h and omega f of the angular velocity. So some regions shrink here, but basically this is the same picture from a little bit far away. So then what we did was, and here I'm just representing studying holography, is to identify very briefly and what the field theory content could be. So we did pick some conditions, some consistent boundary conditions that fixed the dual currents and gauge fields in this way. And we found the conductivity of the CFT, which is this number here. This equation is represented in here. So L is the ADS length, R plus is the value of the horizon for BTC, and this combination here is this gamma that involves both L and omega h, and this is the angular velocity for BTC black holes. So this is what we established then for the holographic content of the solutions in the BTC case. So I wanted to, instead of going very deep into a particular solution, I wanted to also show you that we found as well solutions in ADS4, which was one of the questions, giving 2 or 3 papers in the literature that stated that no energy extraction was possible in 4 dimensions for Kerr ADS for black holes. And so when doing this with Herman and Nelle, we found that there were a few things that we needed to also clarify. And so what I wanted now to show you is the action for these models that one can write from first principles. Then I'm going to show you the generalized solutions and discuss briefly these ideas of energy flux. In particular, the energy flux when we solve within the near horizon regions of the black holes, and how an observer outside from these regions would still see energy extraction. So basically, the action that represents these models, either BTC or ADS, in ADS, spacetime or asymptotically flat, is this equation that we all know. There's the current here, the gauge field, and the field strength. And what happens in the approximation is that the gauge field is nearly independent of the metric. So there will be an effective metric, action that one has to look up. So if
5-minute warning.
Sorry?
5 minutes.
Sure.
Warning, yeah.
If we split the space-times, if you're in 4 dimensions in some toroidal and poroidal coordinates, meaning we will focus mostly in stationary and axisymmetric solutions, we can do a split of the geometry as well, and the gauge field and the current in this way, and find out, if one does this carefully, that the effective action can be rewritten in this way. So the way to find solutions of the problems is to leave the metric or the geometry untouched, or no back reaction in it, and basically finding a field, if it's stationary and axisymmetric, of this form, where omega f is the velocity of the electromagnetic fields, and I here is going to be the current, and one of the components of the gauge fields. And this omega f and I are also just dependent on a phi through this equation. So this is the effective action for the models. It's called the Charlemagne-Waghorn action, and these are the equations where from this action one can derive exactly this BZ model in a more theoretical setup. So what we did, instead of looking at ADS-Kerr black holes, which was a very complicated problem to start with, was to look at the near horizon geometries for the ADS-Kerr black holes in 4 dimensions. I just put here what the expressions are for the typical neck geometry that is of this form, and these are the values. And in ADS, there are 2 different regions that one can construct. One is the typical near horizon region, where one goes to extremality by setting R plus equals to R minus. And there's another region, which is called the superentropic one, that is the one that one can find when one takes the parameter A in the Kerr ADS black hole to be equal to L, the cosmological length. So these are the focus of the solutions. We worked by ansatz. And so this, to find these gauge fields, we proposed that the ansatz should have splits like this. We call them scaling ansatz and logarithmic ansatz for the solutions. And we plugged it in and solved the equations in there. Now, we were finding that most of the solutions had some energy extraction, but then there was the question of whether this energy extraction that we were finding in the near horizon region was really the energy that an observer in the region outside would really see, meaning would this energy flow out from this very big, large throat. And so we came up with a toy model and thinking that actually the process that we usually use in making the coordinate transformations that mix the T and the phi directions to go to the near horizon regions could be explained or thought as moving from some coordinates to a rotating frame. And this is the argument we presented. And as a measurement of the energy flux that we found, that mixed the rotational energy in the neck geometry with the angular rotational energy of the black hole. And what we argue is that this energy is going to be actually the energy that an observer outside from the neck region would measure. So we did check that the exact solutions in the near horizon geometries for BTC that we had found with TED are energy extracting, and we were obtaining with this toy model exactly the energy extraction in the same way as one would define it from different observers in the BTC black hole. And then this is basically the 3 plots that have the energy extraction in the different cases. This is the solution for a solution of energy extraction in the near horizon extremal care. So this is the flat case. This is where the black hole, or what is left from the black hole, is. And so you can see the fields the energy flux that is coming out mostly on the poles. And then on the equator, there's a lot of energy that is coming out in this representation. This is for ADS and care, near horizon extremal ADS. And this one here is for these super entropic ones. And we also find energy extraction for these solutions as well. Perhaps a more, a different way of representing these solutions. These are the pointing fluxes. This is the event horizon. For the near horizon extremal care, here you see some reminiscence of the ergosphere, and these are the fields that we find. And in the cases of ADS neck and SE neck, so the superentropic cases, we see that the outflow happens mostly within the region closer to the black hole and not on these regions as in the care black holes for these solutions that come out in some way. The energy is coming out basically from the regions along the equator. So this is what I wanted to discuss or present today. So muchas gracias.
Okay, thank you very much for a very nice and interesting talk. We will have time for questions now, but remember, after the questions, we are going to take the conference picture. So I'm going to tell you more about that. So, yeah. Well, I have a question, maybe naive. Sorry. Eloy, I guess, has a question. Go ahead.
Thanks. You hear me?
Yes, we can hear you.
Okay. Thanks for the talk. My question is related with the following. Can you comment a little about the back reaction of this configuration? Because we know from LAWGH theorems that the astrophysical black hole must be described by the Kerr black hole. This is the prediction of general relativity. But how sure we are of this magnetic field that produce this jets are really prop fields on the Kerr gravitational field? We can put a sort of limit on this vision.
So the model does not contain any back reaction on the geometry. It ignores it completely. if that is the question. Now,
No,
one
no,
could...
I understand that, but you can
Right.
comment a little on how we can approach to this, try to answer this question.
Right. So in general, we think, so if there would be some back reaction, you would expect the black hole to have some charge in the end, right? Because it would become charged in some way. And this is a process that we don't really understand how it really works, but mostly from the observations, we think that most black holes would be uncharged and neutralized in some way. Now, how this happens dynamically, or how the process is, basically, I think we don't really understand them even numerically in how to do this. One could do a computation basically and say, well, I want to compute, now that I have the field, what is the back reaction and on the geometry. I haven't seen too much of this kind of line in looking at that, but there will be probably a way to do this. But I don't think currently we think that the back reaction would be relevant. There would be an additional process that would neutralize the field. Let me also, because I mixed a bit what happens, I'm only considering the electromagnetic fields. And while the numerical GR guys can look at more complicated processes, I don't have really a disk of matter here. Okay, so this is basically just the geometry and the background electromagnetic field. To do a more realistic approach, one would still have to think about how to incorporate these disks of matter that are behind the black holes. Okay, but even though this process or this model is a simplified version, we think, at least also from the numerical studies, when they set it up and let the evolution proceed, that the fields organize close to the black holes in this way, and they would be constrained with this force-free constraint. So this is all I can tell you, Aloy. I don't know really what the full dynamical process is in how the geometry interacts and then balances when they're doing the more numerical kind of studies, or even in more astrophysical setups.
Thanks, Maria.
Okay, so we have a question by Carlos Núñez. Okay, there are two Carlos.
You had a question, and actually mine was very qualitative, so I leave it for Carlos Cardona, Julio Oliva, and there is a nice question in the chat that.
Okay, let's go to Carlos Cardona.
So go for it. Go for it. So no, I will not say it. You go for yours or Carlos Cardona.
Yeah, let's go Carlos Cardona. Yeah.
Okay, let me take over then. So hi, Maria. It's nice to see you again, even though in these circumstances. Thank you for your talk. So my question is perhaps very simple-minded as well, and I just want to know if you can comment a little bit more on the holographic description of this effect, at least in ADS3 case, if you can say something more.
Yes, so the first question was whether it was even possible, and we didn't go very deep into trying to understand the holographics, and even in 4 dimensions, we didn't, the paper we wrote was merely just a proof of can we find solutions. So what we found that perhaps I did not say here is that the content for the thermal state is not a conformal field theory, it's more a field theory that has a Hawking temperature, and it does have a current, and with the identification of the boundary conditions that we chose, we found this content for the boundary fields. As you can see here, this gauge field, this is the boundary gauge field, is time dependent as well. And this phi dot, even if I we are painting it as a dot. It's a constant. So basically, is it too small, Carlos? Sorry, I took the. So this is what we find for the gauge field. We haven't explored more than what is summarized in here. There's a current as well that is electric, and there's some other azimuthal component in there, and so mostly what we found is related to this. Whether this is a typical gauge field, which is in the dual, that it's time dependent, and how this description from the field theory side looks, or what is really happened, we haven't thought more about it. We just presented the computations, and that was mostly what we did with this, Carlos. So.
All right, still sounds good. Thank you.
So we have a question by Julio, but in the meantime, can you start turning on your cameras for the picture? So Julio, go ahead.
Okay, thank you. So I have a very basic question. Maybe I'm missing something, but when you consider BTC black string, that isn't a solution of Einstein equations. So how do you bring in that metric?
Yeah, this case was mostly a very general case that we wanted to be able to create additional space. It was very hard to find the solutions. It wasn't very easy to find the BTC black hole. So and yes, we don't. This here was not a solution of Einstein's equations. So it's merely a trick in trying to think that perhaps we do have kind of a cylinder type of black hole, and then we could pass through this cylinder, that it's not a solution of Einstein's equations, a current inside of it, and then make a reduction on the z direction, so that we could find the solution to the three-dimensional space. Okay. So, but yes, we did not require for these solutions to in the four-dimensional case to be solutions of Einstein's equations.
Okay, so you are solving the force-free system, but without Einstein equations on a metric like one.
Right. For the four-dimensional case, yes. When we do the, say, reduction or the interpretation for the three-dimensional case, now it's fully three-dimensional. There's no additional field, no matter, no additional anything. The BTC is just purely BTC with its Einstein's equations. There's no back reaction here. And the field solves exactly Maxwell's equations in the background of a rotating BTC, uncharged BTC. Okay, so this Q here is the field strength, basically, or how strong the field is, and not related to any charge, basically.
Thank you.
Okay, thank you very much. So Maria, maybe you can finish sharing the screen, and if everybody else can turn on the camera, Elena maybe can say, we'll take the picture. And
I am not allowed to share to turn on the camera. I don't know why. Maybe
you are not.
You didn't like my talk, and now you.
I didn't do anything.
Okay.
I didn't do anything.
Turn on my camera because it was taught by the host.
Okay. So let me. So to all the co-hosts, please, if you.
Thank you.
And smile. 1, 2, 3. Cheese. And second screen, cheese. And one more, cheese. Okay. Let me go back to the first one because it was once more. Cheese, everybody. Okay, thank you. That's it.
okay, so we thank you, Elena, for the picture, and we thank all the speakers of this session and invite them to the discussion in the afternoon. There are a few questions for Maria that we couldn't ask, so we finish here. We take 5-minute break, so I don't know, we'll come 25 past the hour, and Alberto Farashi will be the host. Okay, we have bye.
Thank you, Martin.
And 5 minutes.
Okay, so welcome back, everybody. So our next speaker is Julio Virueta, who will be talking about the quantum null energy condition on entanglement growth. So Julio, please take it away.
Okay, thank you. And first, let me thank the organizer for this great workshop. It's unfortunate we don't get to see each other in person, but it's great that we can communicate and keep in touch even in these times. Okay, so indeed, I'm going to talk about this, I think, huge result about how to use the quantum null energy condition to constrain to some degree the dynamic of entanglement entropy. So yes, first I congratulate whoever came out with the acronym. It's cheesy. And this is work based on this paper with my collaborator, Mark Massey from the Simon Center. So a quick outline of my talk. I'm gonna give some goals and motivations. I'm gonna remind people or present people who don't know what the quantum null condition is. Then I will give a very quick proof of this new bound we have, and after that I'm gonna rederive the same bound using holographic methods. This will not only be a nice check, but will also give us a couple of additional results that I found interesting, and I'll give some quick summary and some work that is still pending. Okay, so let's start. So positive energy conditions are of great importance in relativistic field theory. They underline many famous results. In particular, in general relativity, they lie at the core of many famous theorems. The Hawking-Arian theorem, the focusing, the fact that normal matter cannot create transversal wormholes, etc. Unfortunately, QFT, we know, allows for local violation of the null energy condition and other energy conditions. Fortunately, in very recent results by many people, including the ones, but not being all the ones I mentioned here, a new proposals exist now for how to generalize the null energy condition for the case of quantum theory. It so happens that even though locally the expectation value of the stress tensor can acquire negative values, those values are bounded by below by this second variation of the entanglement entropy. So I think the picture tells more than what I'm saying. So what we consider is a region where our stress tensor lives, and we consider a null variation of it. So we have this region green, and if the green in the bottom is given by this embedding capital X mu of y, and then we consider a variation along a null vector k, and the change of entanglement entropy, the second change of entanglement entropy, when we do this modification of the entangling region, bounds the expectation value of the stress tensor contract with the same null vector with the variation with. Something to mention here, I wrote the condition in this integral form that doesn't look very local, but one can rewrite this condition in a more local looking fashion using, instead of normal derivatives, using functional derivatives, but this is the form that will be more useful for the purpose of this talk. So the question is, can we use this new quantum null energy condition for something in the same way that the classical null energy condition has many interesting applications? So something we can do is we can turn the logic around of how QNEC was postulated, and instead of using entanglement entropy to bound expectation values of the stress tensor, we can use the expectation value of the stress tensor to bound entanglement entropy in certain scenarios. So the dynamics of entanglement entropy after quantum quenches is a topic that has been much studied since some time ago. It provides a lot of interesting insights into the dynamic of strongly interacting systems and how they reach equilibrium. People have understood since a long time ago that for long enough time, entanglement entropy seems to grow linearly, and a lot of thought and work has been put on understanding this linear growth from the quasi-particle pictures, the tsunami entanglement entropy, and recently membrane theory. But something that has been a little bit less studied or a little bit overlooked is that at early times, entanglement entropy has a quadratic growth. The transition between these two regimes is actually interesting. It gives a sense of the scale for local equilibration. So for the green region, we expect things like hydrodynamics to work or other effective theories, and the red region does not, okay? So we can use the quantum energy condition to provide a bound to the coefficient that determines how fast the quadratic growth happens. This was first proposed by Orazio Cassini in 2016 and relates this coefficient with the energy and pressure of the system once it reaches equilibrium. Okay, so our main goal is to use the quantum null energy condition to prove this bound. Okay, so this is the scenario we are going to consider. Very similar to what I showed before. We consider half space entanglement in some highly excited states, and we consider the null variation of the entanglement region. In this case, it's just along some null vector k mu, which I show here. And then the null energy condition that I wrote before just reduces to this quantity here, where the d++ is your second derivative across the null direction. The null direction formed by the coordinates x1 and t. Okay, and then it's pretty much done. It's quick and dirty. So if you imagine the initial state has translational invariance, the derivative just becomes a time derivative. And furthermore, if you imagine that the initial state has time reflection symmetry, you can do an expansion in time where the first coefficient is always going to be t squared, and then you get the bound. Okay, so that was rather quick. Something one can wonder is this bound actually significant, in the sense that maybe E plus P is some extremely large quantity that, sure, that coefficient is smaller than it, but so what? So a bound is most interesting if we can show that it's a tight bound. With tight, what I mean is that it saturates for some particular configurations. So it so happened that our bound is indeed saturated for a very specific configuration of for a global quench, what is called a global quench or a conformal boundary state quench that has been studied since a long time ago. Okay, so we can check first for d equals 2 theory with conformal invariance. The calculation is well known what the entanglement entropy for that global quench is, and indeed we can check real quickly doing an expansion that the bound is saturated. As a matter of fact, for d equals to 2, we have a very strong constraint which holds for all times and is given by this equation. So entanglement entropy for conformal field theories in 2 dimensions is very, very constrained in this way. So it could be that desaturation is just a phenomena in d equals to 2 for conformal field theory, but I will show later in the talk that desaturation can be generalized for higher dimensions, and so our bound is indeed the best possible bound one can hope to obtain in this general situation. So this is what I mentioned. So unfortunately, conformal symmetry is not as constrictive in high dimensions, so we need to use other methods to derive the bound, to show that the bound is tight, which is we are going to use holography, and in the process we are going to rederive the bound just in purely holographic grounds. Another question one can ask is what happens for more general entangling regions. In the previous quick derivation, I used the half space, which is a very specific, very symmetric configuration. The short answer is that we don't know. The bound for more general regions is not as clear. We can do some progress. So we don't know, but we can do some progress in the particular case of theories with conformal invariance. So for conformal invariant theories, there is a stricter version of quantum Lorentz conditions that we can use. And in particular, we can use the fact that we can map the half space to the sphere to provide a new bound, which is this. Okay. So if you just evaluate these as before, you get this dirtier bound because you have this term that informs you about the particular entanglement structure of the initial state. So for general states, this term is just there and we cannot do anything about it. But maybe some states, for example, a state that respect conformal invariance or stuff like that, where this term will vanish. Okay, but this is a problem that we have. In general, the bound is dirtier for general surfaces. Something interesting is that if the surface is very large, one can very large in comparison with the correlation length of the theory, is that one can imagine this term just being irrelevant, and then we recover our original nice bound. But for general surfaces, it won't be that easy. Okay, so as I mentioned, we would like to check that the bound is tight in arbitrary dimensions, and in one go we also rederive the bound. Okay, so we consider the same setup as before that we saw. In 2 dimensions, the bound is saturated by the conformal boundary quench. This conformal boundary quench has a well-defined, well-understood holographic dual due to Harman and Maldacena. And I won't go through the careful derivation, but you all know you just need to compute the length of this purple holographic entanglement of the surface, which is HRT surface, that happens to end on this end of the world brane that prepares the state. And then you have these 2 formulas. So T is the time and S is the entanglement entropy. So you have a parametric relation between entanglement entropy and time. This has been widely studied for the case of Schwarzschild ADS black holes, but we can imagine more general black brane geometries given by this metric, where A of C and B of C are some arbitrary functions up to some conditions on the boundary. We demand this geometry reduces to ADS in the boundary, and we also demand that it has a horizon so that we still have the same prescription. Okay, and then it's all very easy. The only thing you need to realize by analyzing those 2 equations is that the early time regime is captured by the limit where this parameter tends to 1 from above. So in this same picture is when this surface is very low. Okay, so the part of it that crosses the horizon is very small. Still, it has to cross a little bit, but we can take the limits. Okay, and so one can do an expansion of those equations. It's a little bit messy. You need to be careful because the equations are divergent across the horizon, and one needs to do some regularization. But that's well understood. One just needs to do an integration extended into a complex plane a little bit. That way, one ends up with parameters like this. But this quantity in the parentheses is totally finite. Okay, one is careful with how to do the integration across the horizon. And sure, it looks ugly, but don't be too quick. We can massage this expression a little bit. So what is the key input we are going to use derive the bound, we need some constriction, okay? While in the pure quantum field theory case, we have the quantum energy condition. In holography, what we do is we assume that the geometry, or rather the matter that supports the geometry, satisfies the null energy condition. So that gives you these two inequalities for these very specific ansatz of the geometry we have. And these equations can be easily treated as just some differential equations by putting some positive sources in the right-hand side. Okay, and as I mentioned, we demand very specific boundary conditions that give us ADS in the boundary and a black hole in the at a position that is arbitrary, but we set to 1. Okay, so the thing we do is we just solve these differential equations. That's a very easy exercise. Here they are. Here Q and S of C are the positive sources that I mentioned. So they're arbitrary positive functions. We demand that they have no singularities or something like that. But other than that, this is the general solution with a black hole. Okay. Then what you can do is you can do some lowbrow analysis to find some quantities that are always positive. And so you can relate, once you have your solution, you can use holographic renormalization to compute E plus P. It so happens that E plus P is a combination where you don't need to worry about the particular way you do holographic renormalization, the way you choose your counterterms. And so that's a nice thing. I want to obtain this expression. Okay. So now you just put everything together. One just put everything together and very carefully begin dropping stuff. So we have an expression for S2, this thing I wrote before that was kind of ugly, was an integral. But we know we can check carefully what can we drop, and we do so and we get the inequality. Okay, and it so happens we obtain the same inequality as before, where the saturation happens precisely for the vacuum solution, which gives you ADS Schwarzschild. So this generalizes what we saw in D equals to 2, that the boundary state quench saturates the bound. So indeed, this bound is the best possible scenario one can hope for. Now, this seems as if we just rederive the same thing, working a little bit too hard. The other derivation took 1 slide, this derivation took 3 slides. But we can also do something else using holography. What else can we do? We can consider other famous quench scenarios. Remember, one assumption in the derivation was that the initial state that is prepared by the quench has translational invariance. So the immediate thing that comes to mind is the Badia quench, okay, that has a very nice dual as a formation of a black hole by the collapse of dust, pictured here by this Penrose diagram. Okay, and again, we consider the HRT that calculates entanglement entropy for half space. And something interesting happens here. I didn't include the details, but the derivation is pretty much the same. Something interesting that happens here is that one obtains a tighter bound. Again, saturation occurs in the usual Badia setup, and this has been well studied by this paper by Liu and Su, and they have an expression that is exactly this in saturation. Okay? But we see this bound is a more constraining bound by a factor of 1 over D. So that could be a curiosity, but at least that's the result. Previously, there has been some numerical evidence for this same bound in studies of the formation of ADS Schwarzschild Badia, and they found what they thought was rather curiously this factor of a half, and we just show how you can rederive that same result from the quantum energy condition. However, this is a little bit frustrating we don't have a QFT only explanation of why this factor of 1/d occurs in the specific case of Badia, of the Badia quench. It will be interesting to see if we can get some information about the field theory that where you do your quench, or if we can obtain some insights of what is special about the Badia quench in non-holographic setups. Well, that was rather quick. So I will just go to the summary and outlook. So what we have just done, we provided what we call it, we think is the first purely quantum field theoretical application for the recently proven quantum Lorentz condition. What we did is we reversed the logic of QNEC and use it to bound the dynamics of entanglement entropy at early time. And furthermore, we show that this is the best possible bound one can obtain in this general setup, with the caveat that for the particular setup of Badia quenches, we have an even more restrictive bound. Okay, so there is a lot of work to do, and I would like to discuss a little bit about this. So the immediate problem that I already mentioned is that it's not clear how to generalize this for arbitrary entangling regions. Something funny is that in the derivation of the Badia quench, it's not too hard to imagine how it can be generalized to arbitrary regions. In the original paper by Liu and Su, they show the result holds for arbitrary entangling regions, and one can follow the same procedure using OR bound and show that it holds for arbitrary regions. But as I show, in more general scenarios, there is one needs additional information about the entanglement structure of the initial state. Another interesting problem is if we can extend this result to know something extra about the linear regime. Very lowbrow, you can see why QNEC is not really useful in the linear regime, at least in this first approach. It's a second derivative of something that is linear. So QNEC doesn't seem to constrain the linear regime at all, but it would be interesting if it can tell us something about the local equilibration time, in which we have a transition between the quadratic regime where time reversal symmetry is respected, and the linear regime where the chaotic dynamics have made that effectively we have lost time reflection symmetry. I mean, another interesting problem is in the holographic calculation. This is what I have been pestering one question yesterday. I think it will be interesting to see how quantum corrections affect the saturation. Of course, the bound was derived in quantum field theory without reference to holography, so it holds for quantum corrections as well. But it will be interesting if we can engineer new states or new quenches where the bound is again saturated, and maybe this can teach us more about the physics of how to prepare initial states. And as I mentioned, we would like to explain how the enhanced bound for Badia translates into information about quantum field theory. And of course, the final dream will be if there is an experimental confirmation of this. I mentioned this because there have been recent papers where they have, in condensed matter physics and in whole atom physics, where they have shown that the linear regime indeed behaves as we would expect. So I believe the technology is not yet there, but it will be a nice result if this can be also confirmed experimentally. Here again, I use the fact that the bound was derived in very general features, very general setups, and it holds for anything that can be described by quantum field theory. And that's it. Thanks. I think I was ahead of time.
Okay, yeah. Thank you very much, Julio, for that interesting talk. Yeah, we have plenty of time for for questions. So please raise your hand on the chat if you have any questions for Julio. So none of the usual suspects. So Juan, yes, please go ahead.
Hi. Just a quick question. Does QNEC rely on Lorentz invariance? Or does it work for any QFT, or it has to be like a...
You're asking if it holds like for core QFTs on curve space?
No, for example, non-relativistic theories or things like that.
No. You need to go back to how QNEC is derived, and it's a little bit complicated, but it relies on causality. It's a way to derive QNEC is to study correlations of the stress tensor in some general states, and it requires certain constraints on the OPE of the stress tensor with operators, but and one can use causality to bound those, but I don't believe it requires Lorentz invariance.
But can you imagine deriving similar bounds for non-relativist theories, at least for those with holographic duals, using kind of the same as you did?
Yes, I think you can. I don't think you really need Lorentz invariance. We use Lorentz invariance, but I don't think you need it.
Okay. Okay, thanks.
Cesar, go ahead. Are you there, Cesar?
Yes,
Sorry, yes, I was muted, sorry. Okay, so my question was related to the saturation part of your story. In particular, I was wondering about the saturation of the QNIC per se. Just some papers come to my mind is this papers that says that there's some kind of genetic conditions, QNIC is saturated. Then there is a connection between energy and entanglement. So I was wondering if saturation of QNIC will imply saturation of your bound, or those are just, in some sense, different things.
Saturation of QNIC will imply what?
The saturation of your bound that you derive. Sorry, whether the saturation of QNIC will imply a saturation of the bound that you derive from QNIC. Is that obviously correct, or it's not correct? Or those are independent bounds in some sense?
I'm not sure because of how this bound is for dynamical states. I'm aware of this paper you mentioned where I think it's called energy equals entanglement, energy equal entropy, in which they studied static scenarios, and indeed for everything but everything strongly coupled, they show that the bound saturates. Okay. So that kind of contradicts what I just said, in the sense that I have a lot of scenarios where a lot of holographic scenarios where my bound does not saturate.
Yeah. Okay. Or maybe said differently, if you have a situation in which your bound saturates, would that implies that the QNIC is also saturated or not? Do you know if there is an implication in either way, or?
The problem is that QNIC is much stronger than my bound, in the sense that QNIC is a quasi-local statement that is really independent of entangling region. In QNIC, you only need the entangling region to include the stress tensor, but you don't really care what that entangling region is, right? Mm-hmm. While for entanglement entropy, we do require the shape of the entangling region is very important, because it determines the entanglement structure of the initial state you have, which is what I have. So what I'm saying is, for general regions, you will get these additional terms that I show for the sphere. And if you include those, maybe the bound saturation at all times is QNX saturate, but I will be careful with just saying S2 is less than E plus P.
Okay.
Right? Yeah.
Okay, thank you.
The full, it will give you information about the full dynamics of entanglement entropy, but not about the PCS. When you constrain it to the T-square behavior, it may not.
Okay. Okay. Thanks. Thank you.
Okay, thank you. Next question is from Alfredo. Go ahead.
Okay, thank you. Julio, it seems to me that in order to achieve the goal you have mentioned in your work to do, when you plan to relate this QNEC to cold atoms or condensed matter systems, you need to modify a little bit your approach, because in that kind of systems, the Lorentz invariance is broken. And actually all of these systems that are shown to be non-relativistic in the sense that they have a scale symmetry, but they are not Lorentz invariant. I think it would be very interesting to generalize this approach to this kind of non-relativistic systems.
Yeah, this goes back to what Juan was asking. And if I am picky with where did I use Lorentz invariant, it may be easier to see why it can be easily generalized to non-Lorentz invariant cases. So really, in the only place where I used Lorentz invariant is here. Shut it, blocking myself. Yes, I didn't delve too much into this, but wanted to be careful when do holographic renormalization about which contra terms you add. If you use Lorentz invariant, you can convince yourself that when you consider this particular combination, it doesn't matter because all the contra terms eventually, when contributing to this quantity, are proportional to the metric, which is in Lorentz invariant, the null projection of that is just 0. So more generally, this is where I will search for possible problems. But since the bound can be derived without using holography, I believe it will be still applicable for non-relativistic systems. That indeed, I agree, is what I would need if we hope this to hold in condensed matter systems.
Hopefully.
Okay, thank you. Are there any more questions for Julio? Okay, so if there are more questions, let's thank Julio again for that great talk. So now we're gonna take a break, and then Elena's gonna lead the gender panel. So I guess let's take a break until 1:05 Texas time, if that's fine by the organizers. So
perfect.
I guess a 7-minute break to start the gender panel. So thank you very much.
Thank you, Alberto.
Thanks.
Ale, Antígona y Luciana, ¿podemos hacer algunos tests mientras el break, si es que están ahí?
Sí, yo estoy aquí. Aquí estamos.
Bueno, hola, mucho gusto. Ale, ¿cómo estás?
Bien, aquí estamos.
Entonces
Hola.
yo les hice co-host. Hola, ¿cómo estás? Qué bueno de verte, Luciana.
Gracias.
Hola, aquí Antígona.
Antígona, qué gusto. Primero, antes que nada, muchas gracias a todas por estar acá. Están sacando tiempo de su día y venir a ilustrarnos es súper importante para esta comunidad. Entonces, a ver, las he hecho co-host a las 3. Entonces, las 3 deben de poder compartir su pantalla si es que lo necesitan. ¿Lo van a necesitar? Sí.
Yo sí.
Antígona sí, Luciana también.
Sí.
¿Sí?
Sí.
Ya, ok, perfecto. Entonces, debe de funcionar porque ya son las 3 co-host, pero si quieren lo probamos. ¿Quieren probarlo o así nomás? Como quieran.
Pues yo puedo ver de aquí, puedo ver de aquí compartir pantalla, entonces parece que sí. Perdón, interrumpí a alguien.
Me gustaría probar si anda la pantalla compartida, ¿puede ser?
Sí, sí, sí.
Bueno, voy a probar compartir.
Ok.
Ahí ven mi pantalla. Perfecto. Perfecto, voy a poner... ¿Ahí están viendo?
Sí, todita.
Muy bien.
Ahí está perfecto, sí, muy bien.
Bueno, perfecto. Dejo de compartir entonces.
Ok. Entonces todo está listo. Bueno, como dijimos en los emails, entonces yo les voy a decir una introducción, pero súper breve, o sea, nada más como el nombre de ustedes, dónde están, etcétera, y en orden Ale, Antígona y Luciana, y luego las dejo que empiecen las presentaciones en ese mismo orden, y toda esa parte va a ser grabada, la vamos a grabar, pero luego cuando empiece la discusión, ya no la vamos a grabar, porque nos hemos dado cuenta que nos da, esto de no grabar las discusiones le da más libertad a todo el mundo de expresarse. Entonces, las presentaciones, como son un poco más formales, eso sí lo grabamos y el resto ya queda sin grabar. ¿Ya?
Me parece muy bien. Estoy de acuerdo.
¿Estás de acuerdo? Ok, perfecto. Entonces, esa es más o menos la dinámica y ustedes, bueno, hablen de lo que quieran y a la hora de las preguntas yo me voy a limitar a simplemente más o menos ir sobre los participantes que quieran hacer preguntas y pasárselas a ustedes y, o sea, darles a ellos haz tu pregunta y ya ellos hagan su pregunta. Y yo supongo que ustedes ya son expertas en paneles, saben que... no,
Elena, no sé qué asumes tú de...
pero yo es la primera vez que me he metido a hacer un panel, así es que yo soy la más inexperta de todo esto. Pero acá estoy de moderadora, ¿no? O sea, como si supiera.
Sí, bueno, yo sí necesito moderación, entonces son 10 minutos para cada una, ¿verdad?
10 minutos para cada una, máximo 15 para que haya un poco de discusión, pero luego a la hora de la discusión, entonces, ¿quieres que te avise? Como les puedo dar un warning de cuando te falta unos 3 minutos, digamos, algo así. ¿Quieres que te avise cuando te falta, cuando ya estás llegando a los 10 minutos o no?
Pues sí, si gustas así mandarme un mensaje, o un mensaje, creo que hay mensajes directos para cada participante.
Sí,
Si
pero
gustas me mandas y me sale aquí en mi pantalla así de, ya cállate, se acabó tu tiempo.
Ya, ok, si quieres hacemos eso, porque alguna gente prefiere que le diga verbalmente, ¿no? Es lo que hemos estado haciendo en las charlas, te faltan 3 minutos, te faltan así, no sé, como tú prefieras, porque depende de tu setup, dónde te sale el chat, ¿no? Yo no sé.
A mí me sale un mensajito así como un pop-up que sale
okay.
y entonces
sí
lo veo.
Ya, perfecto. Y luego cuando haya las preguntas de la gente, nada más se las paso a ustedes y si es una pregunta en especial que digan, digamos, para Antígona o para Luciana, entonces ya ustedes la contestan y si no, cualquiera la contesta lo que quiera, ¿no? O sea, me parece que la discusión es mientras más informal y más libre y más, qué sé yo, free form, es como más útil también, ¿no?
Sí, estoy de acuerdo, estoy de acuerdo.
Sí, no hay por qué hacerlo así tan súper rígido. Entonces, va a ser una experiencia interesante porque, Ale, tú estuviste en el panel de strings, ¿no?
Sí.
¿Y qué tal
Sí.
salió eso? ¿Qué tal salió eso?
Salió bien. Básicamente voy a dar una presentación muy similar a lo que di en Strings. Pero no, fue interesante la discusión.
La discusión después fue...
Sí, sí.
Claro.
Al principio la gente es un poco tímida, así que Elena, si quisieras, piensa en algunas preguntas tú misma, si se te ocurre algo, porque
Sí,
va a haber
sí,
momentos de silencio así como awkward.
tengo algunas preguntas de backup que si nadie... No, y ya me han dicho, algunos de mis colegas me han dicho que se sienten intimidados con este tipo de temas. Así es que...
Está muy bien, por primera vez, que sean ellos los que tengan miedo, no nosotras. Eso me gusta.
Sí, sí, estoy de acuerdo. En lo personal me siento un poco foránea porque no, del área no, soy absolutamente ajena al área, así que bueno, no,
Bueno,
creo que
tú y Luciana y Antígona algo tienen de bio en común porque tú haces biofísica y Antígona hace astrobiología, ¿no?
exacto, sí, sí.
Sí, pero bueno, yo fui educada como física, así que conozco perfectamente a la comunidad de físicos, estoy rodeada de ellos, son 70 físicos en el instituto y somos 3 mujeres en física.
Bueno.
Entonces, estoy más que familiarizada con sus discursos y sus excusas.
Claro.
Excusas.
Sí, y toda su misoginia, sí.
Entonces,
bueno.
no sé si ya es hora de... ¿A qué hora dijeron que empezábamos?
Ahora, unas
Ahora.
5 ya están ahí oyéndonos.
Okay.
¿Te parece, Elena, que cuando están hablando el resto de las panelistas, que anulemos el video o no sé, y el audio obviamente es que sí, ¿no? No sé cómo es que disponen ustedes.
A ver, espérate, déjame, antes de que se me pase, mis co-hosts les voy a quitar el co-host para que puedan hacer preguntas. Withdraw co-host permission, Alberto, withdraw co-host permission, Anderson no, Mariano sí, withdraw co-host permission, Tomás, withdraw co-host permission. Ok, entonces, ¿tú qué dices? La forma que hemos estado haciendo las presentaciones es, nadie tiene prendido su video ahorita, ¿ya? Ni su micrófono tampoco, solo nosotras. Entonces, me parece que se puede quedar así, cada uno de ustedes habla, la pantalla va a ir a ustedes y va a hablar. Y luego más bien para la discusión, ya cuando se abra la discusión, entonces ya todo el mundo abre, todos los que quieran, abren su cámara y su, ¿no? Entonces ahorita todo el mundo está muteado y sin cámara. ¿Ya?
Bien.
Entonces empezamos. A ver si me ha llegado algún mensaje por Slack, porque así nos comunicamos. Ya debe ser hora de empezar. Entonces, listo. Sí, sí, sí. Ok, todo el mundo quiere empezar. Okay, so welcome back. We're going to have for the first time in these meetings, we're going to have in these LAWGH meetings, we're going to have a gender panel because we all agree that it's kind of an important issue that we should discuss more often, the problem of gender in physics. We don't usually do. So we're very lucky to have today with us three women that are very active in this area, 3 physicists that are very active in this area. We have Alejandra Castro, who needs no introduction in our community. Everybody is familiar with all her seminal work. And she's also very involved in GenHET, the Gender and High Energy Theory initiative that started in Europe. We also have Antígona Segura. Antígona is, her field is astrobiology, and she is based at ICE-UNAM. And Antígona is very active in advocating for inclusion of women in the exact sciences. Our third panelist is Luciana Bruno. Luciana works in biophysics, and she's a CONICET researcher, and she's a faculty member at the Universidad de Buenos Aires. Luciana is also a member of the Subcomisión de Género of the Asociación Argentina de Física. So the way that this panel is going to be organized is each of our panelists will make short presentations, and then we will open it up for discussion. So Ale, please go ahead.
Okay, I didn't unmute myself. Very good. So you can all see my screen, correct?
Yes. Yes.
Very good. So thank you, Elena, for the introduction. Thank you for organizing this. I really appreciate the platform, the time and the effort that is put into discussing these issues. Now, yeah, perhaps many of you have read a paper of mine. I gave a talk yesterday, but I thought before I dive into the presentation, I might just want to say that, yeah, I'm originally from Chile. The picture that I have right now here, my background is from the region that I grew up in Chile, in Antofagasta. It's the northern part, which I miss terribly. I miss the desert. Since then, I've lived in many different parts of the world, and currently at this moment of time, I'm an associate professor at the University of Amsterdam. But my role today, so for the next couple of minutes, what I'm going to do is describe to you what GenHead is, okay? And then I hope that during the questions and the discussions that we'll have, other topics and things will show up. But I just want to kind of give a little bit of like a commercial on the network. What do we do and how can you be involved in it? So in a very, very brief definition of what GenHead is. So as Elena was saying, this GenHead stands for Gender in High Energy Theory, and it's a permanent working group hosted by the CERN Theory Department, okay? As the name reflects, it's focused on gender and diversity issues in high energy theory, and the group is open to all researchers in high energy theory, okay, irrespective of their gender, across all career stages and all nationalities, okay? So I hope that by the end of this short presentation, you will all feel welcome to subscribe to our network and propose for us new ideas and initiatives or work on those that we're already developing. Now, I want to say a little bit, sorry. So just so you know, here's the website. I will put again I will repeat this website again towards the end, but just because I want to be very explicit, there's a link here. You can all see it. Yes, you can all see it. Okay. I can tell that everybody that is in black is nodding. Yes, so you can subscribe to GenHead right there. Okay, very good. Okay, so the history, how did this all started? So there's actually a few victims here that started this whole thing. So this started as an EU cost action called the String Theory Universe, and it goes back to 2013, okay? So this action, which was basically an action that will fund collaborations and activities, workshops, and conferences, was led by female scientists. These are women that I really respect and admire, so leaders in our fields. And one of the aims of this, basically this action, was to support the development of women, okay? Some of the early achievements of this cost action that was between 2013 and 2017 was basically to generate awareness in the community. This was super important. They basically made gender issues a topic of conversation, something that people had to become sort of aware of and incorporate in their daily work. It was a platform for discussion. It also was very successful at gathering data and statistics. There's very interesting surveys that the cost action created. And something that I valued a lot, so when I moved to Europe, and even a bit before then, was that it was really a place where you could share common experiences, okay? So you could relate to other people in your field, you could have discussions and not sort of feel judged or intimidated by those discussions. And also very importantly, you could share good practices. So if you noticed that there were problems or things in your local group, this was a place where you could like discuss with other people and understand how to basically overcome some of these issues. So it has great, great value as initiated by this action here. Now, since then, so the action was such a success that it didn't go away. So when the funding of that action was completed, it didn't evaporate the whole initiative, and that's where GenHead was created. So in 2018, basically with the great support of CERN, we created this permanent working group, and that's the shape that we have right now. So we don't rely on kind of temporary funding. Now there's a new aspect, so as it became a permanent kind of initiative, it also broadened a bit. So now we don't only cater for high energy theory. So in archive terminology, if I put it in those words, we cater for both what we will call HEP-TH and HEP-PH. So it's high energy theory in a broad sense of the word, so it includes phenomenology. It's also not something that is just about a European collaboration. It has expanded its borders. We have members within the working group that are in North America. We have members in Australia, and we keep on looking for members in other countries. So it's not limited to the European region, although because of historical reasons, most of the members are in Europe. And our objectives at this moment, these are things that we're always discussing and evolving, but in this instant of time, our objectives are the following. So we care about monitoring the situation of women in high energy physics. We want to increase the awareness of gender issues in the field. What's very important also is to improve the visibility and the presence in decision-making roles, so in leadership roles. And also as well provide networking support and mentoring for younger researchers. So what are we doing? So how can you participate or be part of this network besides kind of subscribing to our website? So we're really eager. One of the things that the members of the working group always tell me to reinforce is that we're really eager to connect to other initiatives and networks, okay? So topics of diversity and gender issues are very complex. There's a lot of many different moving pieces. They take a lot of time. And so we're always looking to collaborate with different initiatives and try to help each other and understand and have a broader perspective of what the problems are. So if any of you are part of an initiative, a network, and would like to collaborate with us, please let us know. At the moment, and this was very much initiative by the pandemic because we're all locked at home, there was a big fear of us being very disconnected and not being in touch and not being aware of what was going on because we're all in our tiny, tiny houses. So with that in mind, we started a newsletter, and it basically contains a lot of information just to keep the network connected, to keep you informed, to know what are different initiatives happening in different places. And I'll show you a kind of a sample of like what the newsletter looks like. We're also discussing the creation of webinars that are of interest to our subscribers. So this is in our agenda. We usually, what we do in normal times is that we organize workshops, and we actually we were planning a workshop for this fall, but you can guess, haha, it's not going to happen. So we're going to move very similar to this format, to a virtual format. So this is something that we're trying to implement. Then another very, very important aspect of the network, and it has been doing, and it was part of what the cost action was as well doing, was collecting data and statistics. And this is where I want to tell all of you, since many of you are leaders of your groups, you are institute directors, or you have some kind of important status in your university. The way that we gather data and statistics is that we basically email these people and ask them, can you provide us your numbers? So your collaboration, your input, your support to the network is very important if we want to have accurate statistics of what is happening in our field, okay? So who we are, where we are, and and so this is always an ongoing project, and we're taking it very seriously. If you want to be even a bit more involved, so not just subscribe to a mailing list, but you actually want to be part of this discussions, we do have a Slack workspace, which you can belong to and then kind of see how the sausage is made, basically. So you will kind of be part of our discussions, of the information that we're gathering and stuff like that. So if you're really interested in being even more actively involved, also let me know, and we can discuss incorporating you to our Slack workspace. We also have, so here again, this is the website that you can subscribe to. And we also, since we have some young members that use Twitter, we also have a Twitter account that you can follow. So you can do that. And then just to end, let me just show you a bit. I'll zoom in. So this is a sample of our last newsletter. So it was about 11 pages long. So I just grabbed like a few of these pages so you could see what type of information we're giving. So for instance, what was very important for us for the last month was to discuss the Black Lives Matter issue. We're also trying to cater to the LGBTQ community in our field. We're always supplying some list of reading that we find useful, articles and so forth. There's also actual physics. So we like to just put a collection. So like, okay, what are seminars that you can listen online? If you would like us to promote your conference or workshop, we're also happy to put it in there. We also had a section in terms of like how families were dealing with COVID, how like some of the members of our network were dealing with their quarantine issues. And we also, once we basically profile one of the members of the working group so that you can put faces to this team that is working behind the curtains. So with that, I'm basically done. This is all I wanted to share with you today. Well, and then the questions, of course. Yeah.
Thank you, Alejandra. Antigona, maybe you can share your screen.
Yes, I was trying to unmute myself. Sorry. Let me, here. I just have so many things open here. Just, sorry. Just I have some websites open. So in case somebody wants to ask about some of the resources, I have them right here. So, okay. So let me, oh, I haven't shared anything, right? It's, oh. Can you see? You are seeing my, okay, okay, well, hello, I am Antigona Segura. I am an astrobiologist in UNAM, in the National University in Mexico, which is the largest university, I think, in Latin America. I don't know, but at least it is in Mexico. We have like 500,000 students, almost 500,000 students between all levels, from graduate to high school students. So I'm going to talk about the National Research System, which is a system that includes a lot of researchers, not all of the researchers in Mexico, but it is considered like an honor to be there. But the best thing about this system is that it includes money. So basically, this system was created in 1984 because the salary that we received as a researchers in Mexico was kind of low, especially for some universities, the ones at the States. So they wanted to kind of compete with other countries, making this kind of a scholarship, something like that. So what they did is to create this with 5 levels, from candidate to the emeritus level. Of course, to be emeritus is something that it's very hard to reach, but basically most of the population of this at the SNI, the National Research System, is on the first levels, candidate 1, 2, 3. And each one has an amount of money that is associated with it. And of course, it will be more money as you go up. So this is important, not just because you have this like honor that you are SNE 1 or SNE 2. Some people in Twitter, they have SNE 2 or SNE 2, like it is a big deal. I don't think so, but some people think. But there is the money, and I don't complain about that, of course. One thing that is very important is that it's peer reviewed. So in order to move or to be accepted in this system, you have to go through evaluation that is done by your own peers. So that's very important. So, this is a research that was done where they analyzed 11 years of productivity of the people who belongs to the national system of researchers in Mexico. And this is the last graphic where they basically summarize the result of this research. What they found is that what you are seeing here in the okay, here in black, this is the productivity level of women. In gray, it's the productivity level of men. There are two kinds of institutions here. One is are the centers of research, which belong directly to CONACYT, which is kind of a research, it is the research council in Mexico. And the other ones are universities, public universities, okay? So we have public universities here, research center here in dashed lines. And as you can see, women are always more productive than men, okay? But the funny thing is that when you go to the research system graphics, let me show you. First, we have women. This is the amount of the percentage of women that belong to the national research system. This is the percentage of men. And this is, okay, you can see this is 20 years, from 1999 to 200 to the last year, okay? So it's 20 years. That's, in these 20 years, the amount of women that has been increasing in this research system, it's very, very low. But this is not all this story. It goes here. So let's see the levels. This is level candidate 1, 2, 3. So as we move here, we move to higher levels, more money. And this is the percentage of men up here and women down here. And as you can see, as you move up to levels, women are less in higher levels than men. But I just showed you that we are actually more productive than men, right? But you see what our own peers are doing is basically not seeing this productivity because we are not higher in these levels. These levels supposed to show how productive we are. Basically, they count articles, okay? So for 2019, it was a little bit better for level 3, but for level 2, still the same, right? So we are not moving up in the ladder here in Mexico. And it's the same everywhere, so you can search for this graphics everywhere. Okay, so these are the levels of the SNE, but now they are by the different areas that we have in the national systems or in the national system of research. This is 1999, this is 2019, right? So you can see that the gap is closing, and particularly is closing very efficiently in the areas of medical sciences, humanities, science of conduct. Social sciences are doing better, but then there is this red, orange lines up here and down here. Those are physics, mathematics, and earth science. And the red line, the worst one, is engineering. So let's see, just physics, right? Physics is here. So we have that almost 90% of the people who was in the third level was men, and 10% was women. And it has improved 3% in the 20 years, right? 3% only. So we are doing basically nothing to close the gap, nothing. Because this means that we are not doing anything. So now we have a new government, as many of you know. In Mexico, we have a new government. CONACYT, the Research Council in Mexico, has been highly criticized for things that I don't understand, because I think they are doing a great job. And one of the jobs they just announced, and this is official because this is what you are seeing here, is a publication. It's a copy paste of a publication that is the federal. It's, what do you call this? It's kind of the paper that the government has to announce things that are important, like laws and things like that. So this is the institutional program for the National Council in Mexico, the National Science Council in Mexico, and it has 9 specific actions that include gender perspective, or they are related in somehow to reach gender balance in science in Mexico. I put there 3 of them. One is directed to that PNPC here. That is the program, the national program of graduate programs. So all the graduate programs in Mexico are evaluated and supported by CONACYT. If you don't get into that, your students don't have scholarships from CONACYT. So this is very important. For the first time, CONACYT is asking all these graduate programs to have policies about gender that includes harassment as something that should not happen, must not happen in this place. Okay, so okay, 3 minutes. Okay, so they want to in general generate public policies to close the gender gap, and to promote the respect to the law about the work. We women shouldn't ask for being respected in our work, but it seems that we have to remind everybody about it. So now CONACYT is going to really take care of that, instead of just saying that the law is there for us. So now I'm going to, this is, sorry, I don't know when, okay. This is UNAM. UNAM has the National University has a new development plan that includes gender balance, and they have this program that includes the protocol of against harassment and other aggressions against women, or gender aggressions in general. But this has been because of this. We have students that have been very, very brave. They have been closing the schools because otherwise they wouldn't be heard. They ask in many ways to stop harassment and rape in the university, and the university protected these rapists, these harassers. Most of them are professors. And this is something that is in the numbers, in the what is this report that UNAM did. So this is not my saying, it's a report that is there. Most of the people who is accused of being a harasser or a rapist are professors, male professors. And well, the students did march, they did things like this, which is we called, I don't know how do you call it in Spanish, but in English, but basically we call it tendedero, which is something that we do with the clothes, you know. And so basically they write their experiences with professors or classmates, and they put it there in public for everybody to be seen. It was one in the Faculty of Sciences at UNAM. Some professors were very mad about the truth about them. But anyway, it is there, is the experience of the students, and it's being out. So finally, they were not heard at all at UNAM, and they closed schools. Now, well, there is, we have a new program that includes most of the demands that the students did. And this is something great that the students, the young students in the largest university in Latin America are doing. And that's it.
Thank you, Antigona. Luciana? Antigona, could you stop sharing your screen?
Yes, I'm looking.
Great, thank you. Luciana, estás muteada.
Yeah. Okay.
Okay. Yeah.
No, I was silent, so that's why. So now you see my screen?
Yes, perfect.
Okay. Well, first of all, thank you very much, Elena, and all the organizers for giving us the opportunity to participate in this conference. I'm Luciana Bruno. I'm from the working group of gender working group of our Argentinian Physics Association. And actually, I'm not Claudia Montanari. She was supposed to be here, but unfortunately, she had some health problems. So I sent her my greetings and hope she's okay. So I would like to start with this tweet that appears a month ago here in the middle of the lockdown in Argentina. And it says, it was a Twitter from Scopus that it said that we found that Argentina has the highest women participation in research. So if you can see this, everybody was like surprised about this and cheering. And these results came from a report that was published by Elsevier, which actually explored participation and career progression and perception in order, and I quote, to understand the role gender plays in the global research enterprise and inspire evidence-based policy driven by powerful data. So actually, for example, in their figure 1, you can see they explore the gender dimension within the active authors in scientific publications. And this figure shows that the ratio of women to men is closer to parity on the period 2014 to 2018 compared to 1999-2003 in all the countries. That's a very good news. But to our pleasant surprise, Argentina represents the highest ratio. You see that it's larger than 1. So in some way, it's similar to what Antigona was talking about in Mexico. However, concerning, oops, I'm having some trouble. Sorry, I will stop now. I'm having some trouble. Mhm. Are you listening to me?
Yes. Yes,
Okay.
we can hear you.
I don't know what's happening because my my slides don't go. I will try to share in another.
If you want to share it without the full screen thing, if that
Yeah,
helps, I mean, that's
was
fine.
yeah, that's what I will do now.
Yeah.
Maybe that's so here. Okay. So what you can see if we look at concerning physical sciences, you can see that this analysis shows that women are underrepresented all over the world. You can see, for example, in computer science or mathematics or physics. And that's, well, okay, people say, well, physics and mathematics is difficult. The girls do not like to study these kind of things. But we can ask maybe why, for example, Japanese women that are here, they really don't like science. They hate science, if you can see in all the other countries. So something is making some noise here. We should ask why so few women are studying in these careers. But nevertheless, Argentina has the highest ratio of women. So we are a lot of women in these kind of subjects. However, so now we have this question, why a gender working group in the association is needed. So, and in Argentina, we have like CONICET, that is our National Scientific Council, and we found that women, we represent the 25% of all the researchers in physics. Actually, we are 33% members of our association. But when we have these annual meetings of the association, only 50% of the speakers, of the keynote speakers or invited speakers are women. So putting in another way, it's like we have a club and we pay the same rights to be in the club. We are 33% of us, but when there is a party, only 15% of us are invited. So what message are we giving to our young students, people, new generations, men and women? And so we are not allowed, or in some way we are underrepresented in a way we are just saying, well, you are not invited to show your results, to share your results. So in 2017, in the annual meeting, there were two interesting things that happened. The assembly voted that from now on, at least 30% of the keynote lectures must be assigned to a woman. So now we have this more equal proportion or fraction. And also this gender working group was born. We strongly believe on collective actions to produce changes in a way that also Antigona and Alejandra were talking about. Now, what's the first thing one of our first results service that we did as a gender working group was to analyze what happened with the situation of women in Argentina, physical women in Argentina, in CONICET. And similarly to what Antigona was talking about in Mexico, we find that in 20 years, the proportion of the distribution of women among the different categories from assistant, that is the lower category, to superior, that is the highest category, barely change. It almost remains the same. And not only that, also if we analyze the total number of researchers that are going to the career, we see that the rates that women are going in physics is slower than men. So actually, if we don't do nothing, this will not change. So how can we? Another interesting, well, the most we think that the most surprising results, at least for us and in a bad sense, was found when analyzing the promotion to a higher category. So we found that the fraction of women that get promoted was much lower than that for men. We mean women that are asking for a promotion, they fail in more than men that are asking for a promotion. You can see here that almost 70% of men that ask for a promotion get it, while only 40% of women. So we can ask why. So this is not only bad, but it's getting worse and worse during the years. But if we think that the evaluations are performed in a base of meritocratic standards, we can have a clue of these results. Well, actually, meritocracy is one of the ways that the scientific systems and many other systems have to promote the growing of people in the career. So it's almost well accepted that if we want the more capable people, the more intelligent people, the more prepared people to go to grow in the career, we don't want lazy people, people that don't work to be in the career. Okay, but now there is a question that we ask is, if does meritocracy guarantees objectivity? And the answer is not, or no, sorry. And here we show 3 examples, maybe you may know that, that shows that, that this is not, that, for example, sorry, here I show 3 examples to test the hypothesis of objectivity. And what they do is actually test how blind evaluation works. And I really invite you to read the complete papers and come to your own conclusions, but the results are incredible. I don't know, maybe you can, this is a paper that was published last year in Physics Today, talking about the grants evaluation in the Hubble space-time, or this is the famous John and Jennifer paper, you can Google like that, where some CB evaluations were performed, and the results are really shocking. And also there are some studies on blind auditions in orchestra for musicians that show that women were more accepted when the audition was blind. And not only talking about women, but also other minorities were accepted in the orchestra when the auditions were blind. So actually we think that to evaluate our people more accurately, we need to challenge out implicit hypotheses. We need to become explicitly aware of them. We strongly believe that gender perspective must be one of the requisites that people should have when they are in an evaluation condition. Well, now let me present some of our goals in our association, in our working group. So we intend to visualize the work of women in physics, encourage transversal and collective work, promote network collaborations among women, propose positive actions, mainly for young women, denounce violence and discrimination, and training on gender issues. Many of them are very similar to the ones that Alejandra told about Janet, so maybe then we can share our experiences. And actually we have a webpage that we are actually updating every day almost, and also we are very active in social networks, Facebook and Instagram, thanks to the very enthusiastic young women that participate in our working group. Now the working group is composed by people. We are people from from different parts of the country and different stages or grades in the career. But we try to dynamically renew the members so we can develop a transversal and collaborative work. Also, all the actions and documents and productions that we do, they are also in the page, so you can see all the things that we do. We also organize events, training events to debate and discuss actions that we can do aimed at improving the gender equality. We want to feel comfortable in our community. We want to share our work with confidence and freedom. So we try to make these actions to make this happen. And also a few words about gender violence. Some of us have done some training on this topic to be prepared to give support to people suffering from this kind of violence. More importantly, we are in close contact with experts and institutions that can help women that are suffering from this kind of violence, so we can orientate these people. And finally, one of the projects that we are very enthusiastic about now, it's also related to what Alejandra was talking, and it's that we want to build a network of physicists in Argentina. Now we are gathering all the information and we would like to do an interactive map. So anyone can look in the map and find out other women working on similar topics as scientific, to start scientific collaborations, for thesis advisor or for grant partners. And well, we're working on that. We hope that, we strongly believe that this will be beneficial, not only for women, but also for the whole Argentinian physics community. Well, that was all my presentation. Thanks. Thank you very much. And I can answer questions.
Thank you, Luciana. So if you can share your screen, and now we go to gallery view and we move on to the discussion. And
I think we have